Euentome suicide paradox begins with a gun pressed against your temple, but this is no ordinary gun. It's connected to a quantum device, a machine that measures the spin of a single electron. If the electron spins up, the gun clicks harmlessly. If it spins down, the gun fires a fatal bullet. The twist: the quantum device operates in a state of superposition. Until it's measured, the electron is both spinning up and down simultaneously. You close your eyes, you pull the trigger, click, you're alive, you pull it again, click, still alive, you pull it again and again and again. Click, click, click. No matter how many times you pull the trigger, the gun never fires, the bullets never hit you. But how can that be? Welcome to the quantum suicide paradox, a chilling extension of the Schrödinger's cat thought experiment. In Schrödinger's scenario, a cat in a sealed box is simultaneously alive and dead until observed. In quantum suicide, you're the cat and the observer. Each time the trigger is pulled, the universe splits. In one branch, you die. In another, you survive. But to you, the version that survives, the gun never fires. You keep living endlessly. This concept arises from the many worlds interpretation of quantum mechanics, a theory suggesting that every quantum event splits the universe into multiple branches. In one branch, the electron spins up. In another, it spins down. In one, you live. In another, you don't. From an outside perspective, you're playing Russian roulette with the cosmos, but from your perspective, the gun never fires. You're immortal. But is that really true? The quantum suicide paradox raises fundamental questions about consciousness, probability, and the nature of reality. If every quantum event creates a new universe, does that mean you're immortal in some universes but not in others? And if so, what does that say about death? Is it an end or just a divergence? To understand the paradox, let's break it down. Imagine a scenario where a scientist tests the quantum device repeatedly. Each time they pull the trigger, they either die or survive. From their perspective, they always survive because they can only observe the universe in which they're still alive. But from an external perspective, countless other universes are created where they don't survive. The paradox doesn't eliminate death, it just shifts it to another universe. But what does that mean for you? If you survive every attempt in your version of reality, does that make you immortal? Not quite. You're only quantum immortal, in the sense that your consciousness only perceives the universes in which you survive. The others, where you don't, still exist. You just can't observe them. But this paradox isn't just a thought experiment. It has profound implications for how we think about life, death, and identity. If every decision creates a new universe, then every moment is a branching point. Every you that survives is another version of yourself living in a slightly altered reality. The paradox suggests that you're both dead and alive in infinite universes, each one slightly different from the next. The resolution of the quantum suicide paradox lies in the concept of subjective immortality. From the perspective of the person pulling the trigger, they will always experience survival. But this doesn't mean they're truly immortal. It just means that they're only aware of the universes where they survive, the ones where they don't still exist, just without them. But here's where the real question arises. What if there is a finite number of universes? What if the gun eventually fires in every possible reality? Does that mean even quantum immortality has a limit? And if so, where does the last version of you go when every universe finally closes its doors? Teleportation Paradox begins with a promise that sounds too good to be true. Step into a machine in one location and appear instantly in another. No flights, no long drives, no delays. Just a seamless transfer of your body, mind, and memories from one point to another. But here's the catch. The machine doesn't actually move you. It scans every atom in your body, records the precise arrangement of every molecule, and then transmits that data to a receiver. At the other end, a new body is constructed, atom by atom, molecule by molecule, a perfect copy of you. But what happens to the original? You step into the machine. You feel a slight tingling sensation as the scan begins. The machine hums, then falls silent. In that moment, your body is vaporized, disintegrated down to the atomic level. All that remains is the data, a comprehensive blueprint of everything that made you who you are. On the other end of the world, the receiver begins its work. It assembles a new body, identical in every way to the one that was just destroyed. When it's complete, that new body opens its eyes and steps forward. It has your memories, your personality, your voice, your thoughts. But is it really you? From the outside, nothing has changed. Your friends, family, and colleagues see you step out of the machine and continue your life as if nothing happened. But what about the original you? Is that person now dead, a pile of disintegrated atoms? And if so, is the new you just a copy, a replica that thinks it's you but isn't actually you? This is the crux of the teleportation paradox. It raises profound questions about identity, continuity, and the nature of consciousness. If your body can be disintegrated and reassembled somewhere else, what exactly makes you you? Is it the specific arrangement of your atoms? Is it the continuity of your memories? Or is it something more elusive, something that cannot be captured by data and blueprints? Philosophers and scientists have debated the implications of teleportation for decades. One camp argues that as long as the new you is identical in every way to the original, then nothing has been lost. If the copy has your memories, your personality, your thoughts, and your emotions, then it is effectively you. In this view, teleportation is no different from falling asleep and waking up. The continuity of consciousness is preserved, and that's all that matters. But others see a darker side to the paradox. If the original you is destroyed in the process, then teleportation is effectively murder. The copy may believe it's you, but the original you is gone forever, annihilated in a burst of atomic vapor. In this interpretation, the new you is nothing more than a convincing imposter, a soulless duplicate that only thinks it's you because it has all your memories and thoughts. Consider another variation of the paradox. What if the machine malfunctions? Imagine that instead of disintegrating the original you, the machine accidentally creates two versions of you, one at the original location and one at the destination. Now there are two of you, each claiming to be the real you. Which one is the authentic you? Is it the one that stayed behind or the one that appeared at the destination? And if both are identical, can we even say that one is more real than the other? Now let's take it a step further. Imagine that instead of teleporting you instantaneously, the machine creates a delay. It disintegrates the original you and then stores the data for a week before reconstructing the new you. During that week, you're effectively dead, a disembodied consciousness trapped in a state of non-existence, waiting to be reassembled. But if a week's delay is acceptable, what about a month, a year, a century? The implications of the teleportation paradox extend far beyond science fiction. It forces us to confront the nature of identity and the essence of consciousness. If your mind can be copied, digitized, and reassembled, then what are you really? Are you just a collection of data, a series of memories and thoughts that can be backed up and restored like a computer file? Or is there something more, an intangible essence that cannot be duplicated, no matter how perfect the copy? But there is a resolution to the teleportation paradox, and it lies in the concept of continuity. If we define personal identity as the continuous flow of consciousness from one moment to the next, then teleportation fails the test. The original you is destroyed, and the new you is simply a copy, a convincing replica that thinks it's you but isn't actually you. The original stream of consciousness has been severed, and no matter how perfect the copy, the original is gone forever. Yet this resolution raises a chilling question. If the copy is perfect in every way, indistinguishable from the original, does it even matter? Would the new you feel any less real, any less genuine than the original? And if the answer is no, then WH. What does that say about the nature of reality? And if teleportation becomes a common practice in the future, how would society handle the implications? Would people willingly step into the machine, knowing that they are effectively committing suicide each time, only to be replaced by a copy? Or would they reject the technology altogether, refusing to surrender their sense of self to a machine that turns them into data and then reassembles them like a puzzle? The teleportation paradox doesn't just challenge our understanding of physics and technology. It forces us to confront the very nature of what it means to be alive, to be conscious, to be you. Because if a perfect copy of you can step out of a machine, indistinguishable in every way, then what is the original you? And if that original is gone forever, disintegrated into a cloud of atoms, then what does that say about the nature of death? And perhaps the most unsettling question of all, if teleportation could one day become a reality, would you step into the machine? Would you gamble your existence on the promise that the new you would be just as real, just as alive, just as conscious as the old you? Or would you walk away, refusing to surrender your identity to a process that promises life but delivers death? And if you did step inside, would the you that steps out on the other side even know the difference? Newcomb's paradox begins with a choice. You're standing in front of two boxes. Box A is transparent and clearly contains $1,000. Box B is opaque and you have no idea what's inside. But here's what you've been told. A powerful predictor has already determined what you will choose. This predictor is never wrong. If it predicted that you would take only box B, it placed $1 million inside. If it predicted that you would take both boxes, it left box B empty. Now you have a choice. You can either take both boxes or only box B. What do? You stare at the boxes. The $1,000 in box A is tempting, it's right there, within reach. But what about box B? If the predictor placed the $1 million inside, that would be life-changing. But what if it predicted that you would be greedy and take both boxes? Then box B would be empty, and you'd only walk away with $1,000. You weigh the options. On one hand, if the predictor is as infallible as they say, it already knows what you're going to do. It already made its decision before you even entered the room. If it predicted that you would take both boxes, there's nothing you can do to change that now. The contents of box B are already set. On the other hand, if you take only box B, you're effectively gambling on the predictor's accuracy. You're betting that it truly predicted you would only take one box and that it filled box B with $1 million. But what if it did? What if box B is empty and you walk away with nothing but a bad decision? This is the essence of Newcomb's paradox. It pits two fundamental principles against each other: expected utility theory and causal decision theory. Expected utility theory suggests that you should maximize your gains by taking both boxes. After all, box A clearly has $1,000, and there's a chance that box B might still have the $1 million. Why not take both and potentially walk away with $1,001,000? But causal decision theory suggests a different approach. If the predictor is truly infallible, then your choice is effectively predetermined. If it predicted that you would take both boxes, it left box B empty. If it predicted that you would only take box B, then that's where the $1 million is. Therefore, the optimal strategy is to take only box B and trust that the predictor has placed the money inside. But here's the catch: both approaches seem logically sound, yet they lead to completely different conclusions. Expected utility theory tells you to take both boxes, while causal decision theory tells you to take only box B, and each approach seems to have compelling reasoning behind it. So what do? Imagine you decide to take only box B. You reach out, lift the lid, and find $1 million inside. The predictor was right. It knew you would take only one box, and it rewarded you accordingly. You walk away a millionaire, feeling validated in your decision. Now imagine a different scenario. This time you choose to take both boxes. You lift the lid of box A and pocket the $1,000. Then you open box B, and it's empty. The predictor knew you would take both boxes, and it didn't place the $1 million inside. You walk away with only $1,000 and a feeling of regret. But here's the question: what if you could go back in time and make the choice again? Would the outcome change? Could you outsmart the predictor? Or are you locked into a predetermined fate, one that was set the moment the predictor made its decision? Newcomb's paradox forces us to confront the nature of prediction, free will, and causality. If the predictor is truly infallible, then your choice isn't really a choice at all. You're simply acting out a script that was written before you even entered the room. Your sense of agency is an illusion, a byproduct of your limited perspective. But if the predictor isn't truly infallible, then you have free will. You can choose to take both boxes or only box B, and the outcome will depend on that choice. But that also means the predictor was wrong, and if it can be wrong, then its entire premise collapses. So, what's the resolution to Newcomb's paradox? The answer depends on how you interpret causality and prediction. If you believe in a deterministic universe, one where every action is a result of prior causes and effects, then the predictor's accuracy is absolute. In this view, taking only box B is the rational choice because the predictor has already seen the future and filled the box accordingly. You're simply playing out a predetermined scenario. But if you believe in free will and the ability to make independent choices, then taking both boxes seems like the more rational decision. After all, the money in box B is either there or it isn't, regardless of what the predictor said. The act of choosing doesn't change the contents of the box. However, some philosophers argue that the paradox reveals a deeper truth, that the concepts of free will and determinism are not as mutually exclusive as they seem. If the predictor truly understands your thought process, it can anticipate your decision without removing your sense of choice. You feel like you're making a choice, but in reality, your actions are entirely predictable based on your nature, personality, and past behavior. And that raises a chilling question. If every choice you make is predictable, does that mean you never had free will to begin with? Or, to put it another way, if the predictor can see your future and you can't change it, are you really making a choice at all? The twin paradox begins with two brothers, identical twins. One stays on Earth, living a normal life. The other boards a spacecraft and travels to a distant star at near light speed. Years pass. The brother on Earth grows older, his hair turning gray, his face lined with wrinkles. Meanwhile, the brother in the spacecraft is still young, barely aged at all. When the space-traveling brother finally returns to Earth, he steps out of the spacecraft and sees his once-identical twin, now an old man. The traveler, however, is still youthful, as if time barely touched him. How is that possible? This is the essence of the twin paradox, a mind-bending consequence of Einstein's theory of relativity. At its core, it challenges our fundamental understanding of time. According to relativity, time is not a constant. It stretches and contracts depending on speed and gravity. The faster you move, the slower time passes for you relative to someone who is stationary. Imagine the journey in more detail. The space-traveling brother accelerates to 99.9% the speed of light, heading toward a star system 10 light-years away. To observers on Earth, the journey takes over 20 years round trip, but for the traveler, moving at near-light speed, the experience is vastly different. Due to time dilation, only a few years pass for him. From his perspective, the universe outside the spacecraft is rushing by at an incredible speed, almost like a blur. Time within the spacecraft ticks at a fraction of the rate it does on Earth. For every hour that passes for the traveler, days, months, or even years pass for the twin left behind. But why does this happen? According to relativity, time and space are intertwined, forming a four-dimensional continuum known as spacetime. When you move through space at extreme speeds, your movement through time slows down to compensate. It's as if time is a resource, and the faster you spend it moving through space, the less you have to spend moving through time. To the twin on Earth, it seems as though his brother is racing away at incredible speed. He ages normally, experiencing the passage of years in a conventional way. But for the traveler, moving at near-light speed, time slows dramatically. He ages much more slowly, experiencing only a few years while decades pass on Earth. This effect isn't just theoretical. It has been experimentally confirmed using atomic clocks on fast-moving aircraft and satellites. These clocks, when compared to stationary ones on Earth, tick slightly slower, a real-world demonstration of time dilation. But here's where the paradox gets even more perplexing. According to the theory of relativity, all motion is relative. From the traveler's perspective, it is Earth that is moving away at near-light speed while he remains stationary. In his frame of reference, it is the twin on Earth who should experience time dilation and age more slowly. If both perspectives are equally valid, how can only one brother end up younger than the other? This apparent contradiction is resolved through the concept of acceleration. While both brothers can claim to be in motion relative to the other, only the space-traveling brother experiences acceleration and deceleration during takeoff, turnaround, and landing. This acceleration creates asymmetry in the situation, breaking the symmetry of relativity and allowing for the traveler's time to dilate in a measurable way. Therefore, while both twins observe the other as moving, only the traveling twin undergoes the physical forces of acceleration, which alters the passage of time in his frame of reference. This is why he ends up younger when they reunite. But what does this paradox tell us about time? At its core, the twin paradox reveals that time is not an absolute, universal quantity. It is fluid, relative, and malleable, stretching and contracting depending on speed and gravity. It also raises profound questions about the nature of aging, memory, and experience. Imagine the psychological impact of the twin who returns to Earth. To him, only a few years have passed. He still feels young, his memories fresh. But to his brother, decades have slipped by. The world he once knew has changed, people he loved may have died, and the society he left behind has aged without him. What would it feel like to return to a world that has moved on without you, to a brother who is now an old man, to memories that feel fresh but are now decades in the past? The twin paradox doesn't just challenge our understanding of time, it challenges our understanding of identity and continuity. If time can be stretched and contracted, then what does that say about our lives? Are we just passengers moving through a flexible stream of time, our experiences dictated by how fast we move? The resolution to the twin paradox lies in understanding that time dilation is not a contradiction, but a consequence of relativity. The traveling twin ages more slowly because he is moving through a space at near-light speed, experiencing time at a different rate than his brother on Earth. The asymmetry created by acceleration resolves the paradox and confirms the predictions of relativity. But this resolution leaves us with one haunting question. If time can be bent and stretched, could we one day learn to manipulate it deliberately? Could we travel to the future and return to find our loved ones aged and changed while we remain untouched by time? And if we could, would we want to? Would we be able to handle the psychological impact of outliving everyone we knew, everyone we loved, everyone we once called family? Infinite monkey theorem begins with an absurdly simple premise. Imagine a monkey sitting in front of a typewriter. The monkey has no idea how to type, no concept of words or sentences. It just randomly presses keys, one after another, endlessly. Now, consider this: if the monkey continues typing for an infinite amount of time, could it eventually produce the complete works of Shakespeare? At first, the idea seems ridiculous. How could a mindless monkey, banging away at random keys, ever write anything coherent, let alone the masterpieces of Shakespeare? But when you introduce the concept of infinity, the impossible becomes not just possible, but inevitable. Infinity is a vast, incomprehensible quantity. It's not just a very large number, it's a never-ending sequence, a boundless continuum that stretches beyond any limit. In an infinite span of time, every possible combination of keystrokes will eventually occur. That includes every letter, every word, every sentence, every paragraph. And given enough time, those random keystrokes will line up perfectly to reproduce Hamlet, Macbeth, or any other text you can imagine. But what does this really mean? Imagine the monkey again, typing away endlessly. For millions of years, its keystrokes are a jumbled mess of random letters, but eventually, through sheer probability, the word "the" appears. Then millions of years later, the word "to." Centuries pass and the phrase "to be or not to be" emerges purely by chance. And over infinite time, every word, every punctuation mark, every line of dialogue from every work of Shakespeare will eventually appear not once, but infinitely many times. This is the essence of the infinite monkey theorem. It demonstrates how, given infinite time, even the most improbable events become inevitable. But the theorem isn't just about monkeys and typewriters. It's about probability, randomness, and the nature of infinity. To better understand this paradox, consider a simpler example. Imagine flipping a coin. The odds of flipping heads are 1 in 2. If you flip the coin once, you might get heads or tails. Flip it twice, and the odds of getting 2 heads in a row are 1 in 4. Flip it 3 times, and the odds of getting 3 heads in a row are 1 in 8. But what if you keep flipping the coin forever? Eventually, you will encounter every possible sequence of flips, all heads, all tails, alternating heads and tails, and so on. In an infinite series of flips, the probability of encountering any specific sequence becomes 1, not just likely, but certain. Now apply this logic to the monkey at the typewriter. Each keystroke is like a coin flip, a random event with a certain probability. Given infinite time, every possible combination of keystrokes will occur, including the complete works of Shakespeare. The paradox lies in the fact that something so improbable becomes inevitable when infinity is introduced. But there's a deeper layer to the infinite monkey theorem. What does it say about meaning, order, and chaos? If a mindless monkey can randomly produce a work of art through sheer chance, what does that say about the nature of creativity? Are the works of Shakespeare a product of intentional genius, or are they just one of an infinite number of random arrangements that happen to make sense? Some have argued that the infinite monkey theorem reduces meaning to mere probability, suggesting that given enough time, even the most profound works of art could arise from chaos. But this interpretation misses a crucial point. While randomness can produce order, it does so without intent, purpose, or understanding. The monkey may type the words "to be" or "not to be," but it has no idea what they mean. The words are empty, devoid of context or intent. To truly appreciate the complexity of the theorem, we must consider the implications of infinite randomness. Imagine a universe where every possible arrangement of atoms is realized. In that universe, there would be infinite copies of you, infinite versions of Earth, infinite variations of every event that has ever occurred. Somewhere in that infinite expanse, there is a version of you who is a billionaire, a version of you who is a king, a version of you who is homeless. Every possible reality exists somewhere, waiting to be stumbled upon by the infinite monkey of randomness. But what about the practical implications of the theorem? In reality, we do not have infinite time, infinite monkeys, or infinite typewriters. The sheer number of keystrokes required to randomly produce a single coherent sentence, let alone a Shakespearean play, is astronomically large. The probability of it happening in any finite time frame is so minuscule that it might as well be 0. However, the theorem does have real-world applications in fields like cryptography, data compression, and the study of random processes. It serves as a reminder that in the realm of probability, even the most unlikely events are not impose. Sybil, just exceedingly rare. Now let's address the resolution to the infinite monkey theorem. The paradox itself is not a logical contradiction. It is a demonstration of the counterintuitive nature of infinity. The resolution lies in recognizing that while the theorem is technically correct, its practical implications are negligible. In reality, the chances of a random sequence of keystrokes producing a coherent work of literature are so infinitesimally small that they can be effectively dismissed as impossible. But there is a lingering question. If randomness can produce order given infinite time, does that mean our universe, with all its complexity, order, and structure, is just a product of infinite random events? Are we, in some sense, the result of a cosmic monkey typing away at the keys of existence, producing meaning by sheer accident? And if so, what does that say about our search for purpose? Is meaning something we create, or is it something we stumble upon by chance, like a monkey at a typewriter accidentally writing the words to be or not to be? Imagine a spinning disc, like a vinyl record or a merry-go-round. You're standing at the center, feeling calm and steady. Everything around you seems normal. Time ticks away at its usual pace. But as you move toward the outer edge of the disc, something strange begins to happen. The edge is spinning incredibly fast, almost reaching the speed of light. To you, standing at the center, everything still seems fine. But to someone standing at the edge, time is moving slower. The faster they move, the more time stretches, almost as if it's being pulled like a piece of elastic. But it's not just time that's being distorted, space is also being warped. At the center of the disk, distances feel normal, but at the edge, the distance seems to stretch and bend. The disk no longer seems perfectly round. Instead, it appears distorted, stretched outward as it spins faster and faster. This is the Ehrenfest Paradox, a thought experiment that shows how our familiar ideas about space and time start to break down when we approach the speed of light. It's a paradox that exposes the strange consequences of Einstein's theory of relativity when applied to rotating objects. Now let's break it down further. In everyday life, we're used to the idea that the distance around a circle is simply the diameter multiplied by a fixed number. But when we're dealing with objects moving at extreme speeds, that simple rule no longer applies. At the center of the disk, where movement is slow, everything behaves normally. Time flows evenly, distances are predictable, but as you move outward toward the edge, the speed increases, and as the speed increases, time slows down. This effect is called time dilation. But there's another effect at play, length contraction. To someone standing at the center, the edge of the disk appears to contract, shrinking as it spins faster. But to someone standing at the edge, space seems to stretch. Distances are no longer what they used to be. Now here is where the paradox truly emerges. If the edge of the disk is shrinking due to length contraction, but the radius, the distance from the center to the edge, remains the same, then the relationship between the center and the edge no longer follows the simple, predictable pattern we're used to. The shape of the disk is no longer a perfect circle. It becomes distorted, stretched, and warped by the effects of relativity. But how can a solid disk, made of rigid material, suddenly change its shape? This is where the concept of rigidity comes into play. In everyday life, we think of solid objects as perfectly rigid, but in the realm of relativity, perfect rigidity is impossible. As the disk spins faster, the forces holding it together have to adjust to account for the effects of time dilation and length contraction. Imagine the atoms at the edge of the disk. They're moving at nearly the speed of light. Time is slowing down for them, and distances are contracting, but the atoms at the center are barely moving at all. They're experiencing time and space in a completely different way. This difference in experience creates stress and strain within the disk. The material stretches and compresses in ways that seem to defy our everyday understanding of geometry. The faster the disk spins, the more extreme these effects become. But the paradox doesn't end there. What if the disk continues to accelerate? What if the edge reaches the speed of light? According to relativity, as an object approaches light speed, its mass increases dramatically. It takes more and more energy to keep it spinning. If the disk were to reach light speed, the energy required would become infinite, an impossible scenario. And so, the Ehrenfest Paradox serves as a powerful illustration of the limits of classical physics. It shows how our familiar ideas about space, time, and geometry begin to break down under extreme conditions. It forces us to question what we think we know about the nature of space and time. But what does the Ehrenfest Paradox really teach us? At its core, it's a lesson in perspective. To someone at the center of the disk, everything appears normal. Time flows steadily. Distances are predictable. But to someone at the edge, time is moving slower, distances are stretching, and the entire structure of the disk seems to be warping and bending. This disparity in perspective raises a profound question. If geometry itself can change depending on where you stand and how fast you're moving, then what is the true shape of reality? Are distances fixed or are they relative? Is time a constant or is it elastic, stretching and contracting with speed? And if space and time are not fixed, then what does that say about our understanding of the universe itself? The Ehrenfest Paradox doesn't just expose a flaw in our understanding of geometry. It forces us to confront the reality that space and time are not absolute, that they can bend and warp under extreme conditions, and that what we perceive as solid and unchanging may be more fluid and malleable than we ever imagined. And as you stand there watching the disk spin faster and faster, feeling the edges stretch and twist, you can't help but wonder, if space and time can be warped by speed, then what other illusions are we living under? What other truths are bending and twisting under forces we can't yet perceive? And if space and time themselves are elastic, capable of warping and stretching under the strain of motion, then what is the true shape of reality? Is it fixed and unchanging, or is it a swirling, shifting tapestry of perspective, forever bending and twisting under the forces of motion and gravity? Imagine you're standing in front of a table. On the table are two identical envelopes. You know that one of them contains a certain amount of money, and the other contains either half that amount or twice that amount. You're allowed to pick one envelope and open it. You pick one and open it. Inside, you find $100. Now you're given a choice: keep the envelope you opened or switch to the other one. You pause, thinking it through. If the envelope you opened contains the smaller amount, then the other envelope must contain twice as much, or $200. But if the envelope you opened contains the larger amount, then the other envelope must contain half as much, or $50. So what should you do? Let's think it through step by step. If you keep the envelope you have, you walk away with $100. But if you switch, you could either end up with $50 or $200. You might reason like this: if there's a 50% chance of getting $50 and a 50% chance of getting $200, then the average or expected value of switching would be more than $100. It seems logical that switching is the better choice. But then something starts to feel wrong. If switching is always the better choice, then that would mean that no matter which envelope you pick first, the other one is always better. But how can that be? The envelopes are identical. How can one always be better than the other? This is the essence of the two envelopes paradox. It creates a loop of logic that seems to suggest that switching is always the better option, regardless of what you initially chose. But that can't be right. If both envelopes are identical in appearance, and you know nothing about their contents beyond the general rules, how can one always be better than the other? Let's break it down further. Imagine that instead of $100, you find $1,000 in the envelope. Now, the stakes are much higher. According to the same reasoning, you still feel compelled to switch. The other envelope might contain either $500 or $2,000. But here's the catch: the reasoning that led you to believe that switching is better applies no matter what amount you find in the first envelope. Even if you found $1 million, you would still feel compelled to switch, thinking that the other envelope could contain either $500,000 or $2 million. Now the paradox tightens. You start to realize that the logic is flawed. The mistake lies in the way we calculate the potential outcomes. We're treating the amount in the first envelope as a fixed point of reference, but in reality, that amount is a variable. The moment you open the envelope and see the amount, it becomes your reference point, and the possible amounts in the other envelope are not evenly distributed. Let's look at it another way. Imagine that you don't open the first envelope yet. You just pick one and hold it in your hand. You know that one envelope contains half as much as the other, but you don't know which is which. In that case, the expected value calculation makes sense. You are genuinely uncertain, and both options feel equally likely. But once you open the envelope and see a specific amount, the calculation changes. Now you have a concrete value in front of you, and the possible values in the other envelope are no longer evenly distributed. The logic that compelled you to switch was based on the false assumption that both possibilities, half or double, were equally likely, when in reality they are not. Now let's take it even further. Imagine that you open the first envelope and find $1 million. According to the original reasoning, you would still be tempted to switch, thinking that the other envelope might contain either $500,000 or $2 million. But at this point, the reasoning starts to feel absurd. If you are holding $1 million, how likely is it that the other envelope contains $2 million, and how likely is it that it contains just $500,000? This is the deeper layer of the paradox, the psychological trap. Even after understanding the flawed logic, the temptation to switch persists. The paradox exploits our tendency to focus on potential gains without adequately considering potential losses. Now let's look at the resolution. The key to resolving the paradox is to recognize that the expected value calculation is misleading. Once you open the envelope and see the amount, the original probabilities no longer apply in the same way. The amount in your hand becomes a new reference point, and the potential outcomes in the other envelope are not equally likely. If we think about it in simpler terms, the paradox is a reminder of how easily we can be misled by flawed logic. It shows how the mind can get trapped in loops of reasoning that seem airtight but are actually based on false assumptions. But this raises a deeper question. If we can be so easily deceived by a simple choice between two envelopes, how often do we fall into similar traps in everyday life? How often do we miscalculate risks, overestimate potential gains, or convince ourselves to switch when we should stay put? And if the mind can be so easily fooled by a paradox this simple, how many other paradoxes are lurking in our daily decisions, waiting to catch us in loops of infinite reasoning, urging us to switch when the best choice was to stay all along? Quantum Zeno effect begins with a peculiar idea. The more you observe something, the less it changes. Imagine a radioactive atom teetering on the brink of decay. You watch it, staring intently, waiting for it to emit a particle and decay into something else. But as you keep watching, nothing happens. The atom just sits there, frozen in time, as if your gaze has somehow trapped it in its current state. How can that be? This is the essence of the quantum Zeno effect, a phenomenon named after the ancient Greek philosopher Zeno, who famously argued that motion was an illusion. But in the quantum world, Zeno's paradox takes on a whole new meaning. Instead of preventing motion, the act of observation prevents change. The more frequently you observe a quantum system, the less likely it is to evolve. But how does that work? Imagine a laboratory where scientists are monitoring a quantum particle that is known to decay over time. They set up a detector to measure the particle's state at regular intervals. Each time they check, they find that the particle has not decayed. They keep checking over and over at increasingly shorter intervals, and as they do, the particle remains in its original state, as if frozen in time. What's happening here is a consequence of the peculiar nature of quantum mechanics. According to quantum theory, a particle in a superposition of states doesn't choose a specific state until it is observed. The act of measurement collapses the superposition into a definite outcome. But what if the observations are so frequent that the particle never has a chance to evolve into its decayed state? This is the crux of the quantum Zeno effect. By observing a particle continuously, you can effectively prevent it from changing states. The particle remains in its original state because each observation forces it to reset its quantum clock, preventing it from progressing to the next state. But this effect is not just a theoretical curiosity. It has been observed in real-world experiments. Physicists have used lasers to monitor atoms in a state of potential decay. By increasing the frequency of measurements, they were able to delay the decay indefinitely. The more they observed, the less the atoms decayed, a real-world demonstration of the quantum Zeno effect in action. But why does this happen? The key lies in the nature of quantum measurements. In the quantum world, particles don't behave like billiard balls moving predictably through space. Instead, they exist in a state of probability, a fuzzy cloud of potential outcomes that only resolves into a definite state when observed. The act of measurement disrupts the superposition, forcing the particle to choose a specific state. But if the measurements are constant and unrelenting, the particle is effectively trapped in its initial state, unable to evolve because each measurement forces it to revert to its starting position. It's like trying to catch a runner who never moves because every time you look, he's standing at the starting line. Now let's take this paradox further. What if instead of measuring the particle continuously, we only observe it sporadically? Would it still remain frozen in time? The answer is no. The quantum Zeno effect only occurs when the observations are so frequent that they prevent the particle from evolving. If the observations are spaced further apart, the particle is free to change states in the intervals between measurements. But here's where the paradox deepens. Imagine you are the particle trapped in a state of constant observation. You want to move, to evolve, to change, but each time you try, the observer's gaze pulls you back to your starting point. You are frozen, suspended in a state of perpetual stasis. Is this not a form of quantum prison, a paradoxical state where the more you try to change, the less you are able to? Now consider what this means for the nature of time itself. If observation can prevent change, does that mean that time is not a fixed, objective flow, but a fluid, malleable construct that can be stretched or compressed by the act of measurement? Does that mean that time is not a constant, but a consequence of how frequently we observe the universe around us? The quantum Zeno effect raises profound questions about the nature of reality. If observation can prevent change, does that mean the act of measurement is not just a passive recording of events, but an active force that shapes the very fabric of existence? Are we, in some sense, the architects of time, freezing and unfreezing the world around us with every act of observation? Now let's address the resolution. The quantum Zeno effect is not a violation of quantum mechanics, but a natural consequence of how quantum systems behave under constant observation. The resolution lies in understanding that quantum states are probabilistic, not deterministic. The act of observation collapses the wave function, forcing the particle to chose a specific state. But when the observations are constant, the particle is unable to move to a new state, effectively freezing it in place. But this resolution raises another question. If observation can freeze time, could it also reverse it? Could we, by controlling the frequency of measurements, manipulate the flow of time itself, slowing it down, speeding it up, or even stopping it entirely? And if so, what would that mean for our understanding of free will, causality, and the nature of reality itself? If time is not a fixed, objective quantity but a fluid, malleable construct that can be shaped by observation, then are we truly free to move forward in time? Or are we trapped in a quantum prison of our own making, frozen in place by the very act of looking? Cat-in-the-Box Paradox begins with a single haunting image, a sealed box containing a cat, a vial of poison, and a radioactive atom. The atom has a 50% chance of decaying within the next hour, and if it does, a Geiger counter will trigger the release of the poison, killing the cat. But if the atom doesn't decay, the poison remains sealed and the cat remains alive. But here's the twist. Until the box is opened and observed, the cat is both alive and dead. Not one or the other, but both, existing in a bizarre state of quantum superposition. How can that be? This is the essence of the cat-in-the-box paradox, a thought experiment proposed by physicist Erwin Schrödinger to illustrate the absurd implications of quantum mechanics. It's a paradox that forces us to confront the fundamental question, what is reality? Is the cat really both alive and dead, or is it just our knowledge that's incomplete? Imagine you're the one standing outside the box. You know the setup, you know the probabilities, you know that the atom has a 50% chance of decaying and a 50% chance of not decaying. But until you open the box and look inside, you have no way of knowing the outcome. And here's where the paradox takes a dark turn. According to the Copenhagen interpretation of quantum mechanics, the cat remains in a state of superposition, both alive and dead, until it is observed. The act of observation collapses the superposition into a definite state, forcing reality to choose between the two possible outcomes. But what does that mean for the cat? From the cat's perspective, is it aware of its own state? Is it experiencing both life and death simultaneously, a ghostly half-existence trapped between two worlds? Or is the cat completely oblivious to the paradox, existing in a singular, definite state regardless of our knowledge? Now consider the implications. If the cat is both alive and dead until observed, then what does that say about reality itself? Is reality a fixed, objective state, independent of our observations, or is it a fluid, indeterminate state that only becomes real when we observe it? But the paradox doesn't end there. Imagine a more extreme version of the experiment. Instead of a single cat in a single box, imagine 1,000,000 boxes, each containing a cat, a vial of poison, and a radioactive atom. Each box is isolated, each cat in a state of quantum superposition. Until each box is opened, every cat is both alive and dead. But here's the question: if we open just one box and find a dead cat, does that mean all the other cats are also dead? Or could some still be alive, waiting for their fates to be determined by our observations? This version of the paradox raises the unsettling possibility that reality is not just indeterminate, it is fragmented, a mosaic of potential outcomes waiting to be solidified by our gaze. Each observation collapses one possibility into a definite state, but leaves all other possibilities untouched, lingering in a ghostly state of quantum ambiguity. Now let's take the paradox even further. Imagine that instead of a cat, the box contains you. You are placed inside with the vial of poison and the radioactive atom. The lid is sealed. Outside the box, scientists watch and wait, aware of the setup but unable to see inside. To them, you are now both alive and dead, existing in a state of quantum superposition. But what about you? From your perspective inside the box, you are clearly alive or clearly dead. There is no ambiguity, no superposition, no dual state. You are either breathing or you are not. But from the perspective of the observers outside, you are both a quantum ghost, a living corpse, trapped in a paradox of probabilities. Now let's address the resolution. The cat-in-the-box paradox is not a true paradox in the logical sense. It is a thought experiment designed to illustrate the strangeness of quantum mechanics. The resolution lies in the interpretation of quantum theory. According to the Copenhagen interpretation, the cat is in a superposition of states until observed, at which point the wave function collapses into a definite state. But there are other interpretations. In the many worlds interpretation, the cat is not in a superposition, but rather exists in multiple parallel universes. In one universe, the cat is alive. In another, it is dead. Every observation splits reality into distinct branches, each containing a different outcome. In this view, the cat is never both alive and dead. Instead, there are two distinct realities, each equally real, each unaware of the other. But this raises another question. If every observation creates a new universe, how many universes are there? How many versions of the cat are there, each existing in a different state of being? And what does that say about the nature of choice, fate, and free will? And if we are the ones inside the box, how many versions of us are there, each experiencing a different reality, each unaware of the others? But the most unsettling question remains. If reality is determined by observation, then who is the ultimate observer? Are we the ones collapsing the wave function of the universe, solidifying possibilities into actualities with every glance, every thought, every breath? Or is there another observer, a cosmic eye, watching us from beyond the veil, collapsing our lives into a single, definite reality, or perhaps an infinite array of realities, each as real and unreal as the cat in the box? Earth Day Paradox begins with a simple question. How many people need to be in a room for the chance of two of them sharing the same birthday to be more than 50%? Most people would guess the number is quite high, maybe 100 or more. After all, there are 365 days in a year, so the odds must be slim, right? But the actual answer is much lower. The number is just 23. How can that be? Imagine walking into a room with 22 other people. You don't know their birthdays and they don't know yours. You glance around, looking at the faces, and wonder, what are the odds that two of them share a birthday? At first, it seems unlikely. With 365 possible birthdays and only 23 people, it feels like the odds of a match should be tiny. But that's where intuition misleads you. Instead of thinking about specific people, think about all possible pairs. In a group of 23, there are 253 pairs of people. That's 253 chances for a shared birthday, and when you consider it that way, the probability of a match rises quickly. Now think of it like this. Imagine you're the first person in the room. Your birthday can be any day of the year. The next person walks in. They have a 364 out of 365 chance of not sharing your birthday. The third person walks in. Now, the odds of them not sharing a birthday with either of you are slightly lower. And as more people enter the room, those odds keep dropping. By the time you reach 23 people, the chances of at least two people sharing a birthday is just over 50%. But why does this seem so counterintuitive? The mistake most people make is focusing on a specific person and asking, what are the odds that someone else shares my birthday? That's not what the paradox is about. It's not about you. It's about any two people in the room out of all possible pairs. And with 253 pairs to consider, the odds of a match are much higher than they first appear. Now let's take it a step further. What if there are 50 people in the room? The number of pairs skyrockets. Suddenly, there are over 1,200 pairs to consider. The probability of a shared birthday now exceeds 97%. Add just 10 more people to the room, bringing the total to 60, and the odds of at least 2 people sharing a birthday is now over 99%. But what does this tell us about how we perceive probability? The birthday paradox reveals how easily our intuitions can be fooled by large numbers. We underestimate how quickly the number of possible pairs grows as the group size increases. It's not about the specific days on the calendar, it's about the number of opportunities for a match. Now think of a real-world application of this paradox. In cryptography, the principle behind the birthday paradox is used to analyze security vulnerabilities. Imagine a digital security system that generates unique fingerprints for data, like a hash function. The purpose is to prevent collisions, where two different pieces of data generate the same fingerprint. But just like in the birthday scenario, the number of possible pairs grows quickly as the amount of data increases. Even if there are millions of potential fingerprints, it doesn't take as many data points as you'd think for a collision to become likely. This is known as the birthday attack, a technique that exploits the paradox to find vulnerabilities in security systems. The idea is that even if the space of possible fingerprints is vast, the number of possible pairs grows so quickly that a match is much more likely than it seems. But let's return to the original paradox. Imagine you're in that room with 23 people. You go around asking each person their birthday. The first person says March 14th. The second person says October 22nd. The third says March 14th. And suddenly, there it is, a match. Two people with the same birthday in a group of just 23. The crowd reacts with surprise, confusion, disbelief. How could it happen with so few people? The answer isn't in the specific dates, it's in the sheer number of pairs. Each pair is an opportunity for a match, and with 253 pairs in play, the odds of a shared birthday are higher than most people realize. Now let's resolve the paradox. The key to resolving the birthday paradox is reframing the question. Instead of asking, what are the odds of someone sharing my birthday? We ask, what are the odds of any two people sharing a birthday? By focusing on the group as a whole rather than on a specific individual, the paradox dissolves. It's not about the number of days in the year, it's about the number of pairs. And with 23 people, those pairs add up quickly. But this resolution raises a deeper question. If our intuitions can be so easily misled by simple probabilities, what other patterns might we be missing in our daily lives? How many other paradoxes are hidden in the numbers, waiting to catch us off guard? And if we can be so wrong about something as seemingly simple as shared birthdays, what else are we misunderstood? Anding about chance, randomness, and the nature of probability itself. Shirley Paradox begins with a seemingly innocent statement. Shirley believes that everyone in this room is a liar. You look around the room, observing the faces of those present. You see Shirley staring intently at each person, a look of suspicion in her eyes. But here's the twist. If Shirley believes that everyone is a liar, then she must also believe that she herself is a liar. And if she believes that she is a liar, then can we believe anything she says, including her claim that everyone is a liar? This is the essence of the Shirley Paradox, a variation of the classic liar paradox, but with an added layer of complexity. Instead of a single self-referential statement, we now have a statement that encompasses an entire group, including the person making the statement. This subtle shift creates a logical loop that is far more difficult to untangle than the original liar paradox. Imagine you're in the room with Shirley. She repeats her claim, everyone in this room is a liar. You ask her, including you. She nods, yes, including me. Now the paradox deepens. If Shirley is a liar, then her statement must be false. But if her statement is false, then not everyone in the room is a liar, which means Shirley's statement is true. But if her statement is true, then she is a liar and her statement is false. And so the loop continues, spiraling endlessly without resolution. But let's take it further. Imagine that instead of a single room, we have an entire town. In this town, everyone is known to lie all the time. Shirley stands in the middle of the town square and declares, everyone in this town is a liar. Now the paradox becomes even more pronounced. If Shirley is telling the truth, then she is a liar and her statement must be false. But if she is lying, then her statement must be true and she is telling the truth. But what if there are levels to lying? What if Shirley is not just a liar, but a liar who knows that she is a liar? What if she is aware of the paradox and uses it to her advantage, creating a logical trap that ensnares anyone who tries to resolve it? Imagine Shirley saying, "I am lying when I say that everyone in this room is a liar." Now, we have a statement that is self-referential and self-negating, a statement that simultaneously asserts and denies its own truth. It's a statement that cannot be true or false without contradicting itself. Now let's shift perspective. Imagine that instead of Shirley, it's you who makes the statement. You declare, "Everyone in this room is a liar, including me." Now you're caught in the same logical loop. If you're lying, then your statement is false, and not everyone in the room is a liar, including you. But if your statement is false, then you're not lying, and your statement is true. This creates a form of logical feedback, a self-referential loop that echoes endlessly, bouncing back and forth between truth and falsehood without ever settling on a definitive resolution. It's like standing between two mirrors, watching your reflection repeat into infinity, each iteration slightly more distorted than the last. But what if we take it a step further? Imagine that instead of a room, we have a court of law. Shirley is on trial for perjury. The prosecutor asks, "Did you lie when you said everyone in the room is a liar?" Shirley responds, "Yes, I lied." Now the paradox takes on legal implications. If Shirley lied when she said everyone in the room is a liar, then she was telling the truth about lying, which means she wasn't lying. But if she wasn't lying, then her statement was true, and everyone in the room is a liar, including herself. But if she's a liar, then her statement was false, and the loop continues. But what is the resolution to the Shirley paradox? The key lies in distinguishing between different types of statements, statements about others, statements about oneself, and statements that are self-referential. The original liar paradox involves a single self-referential statement, "I am lying." But the Shirley paradox involves a collective statement that encompasses the speaker, the group, and the speaker's relation to the group. The resolution involves breaking the loop by isolating the self-referential component. Instead of focusing on the entire group, we focus on Shirley's specific statement about herself. If Shirley claims that everyone in the room is a liar, we can isolate her statement as a distinct proposition and analyze it separately. But this resolution raises a deeper question. If we can resolve the paradox by isolating self-referential statements, then what does that say about truth itself? Are all statements inherently self-referential, looping back on themselves in ways we don't even realize? And if so, how much of what we say can be trusted? How much of what we believe is true? And if every statement is a potential paradox, a self-referential loop waiting to be untangled, then what does that say about the nature of language, logic, and reality itself? Is truth a fixed point, or is it an endless hall of mirrors, reflecting back upon itself, each reflection slightly more distorted, slightly more ambiguous than the last? The reverse paradox begins with a simple thought. What if everything you know about cause and effect could work backwards? Imagine you wake up one morning, and instead of getting out of bed and then feeling awake, you suddenly feel awake and then get out of bed. It's as if the effect comes first, followed by the cause. Now imagine this happening throughout your entire day. You eat because you feel full, you laugh because you're happy, and you apologize because someone forgives you. The natural order of events is flipped, and every action seems to follow its consequence. At first, this sounds like a bizarre hypothetical scenario, something that couldn't possibly happen in the real world. But the reverse paradox isn't just about flipping the sequence of daily events. It's about questioning the very nature of causality and whether the relationship between cause and effect is as fixed as we believe. To understand this paradox, let's think about time itself. We perceive time as moving in one direction, from the past to the future. This gives rise to a natural sequence where causes lead to effects. You strike a match and then it lights. You push a ball and then it rolls. But what if time itself could flow backward? What if the effect could exist before its cause? In the world of quantum mechanics, this isn't just a theoretical curiosity. There are phenomena that seem to suggest that cause and effect can be reversed, or at least that their order isn't as clear-cut as it appears. One such phenomenon is retrocausality, the idea that an event in the future can influence something in the past. Imagine a particle moving through space, seemingly influenced not just by past interactions, but by future ones as well. Experiments with quantum entanglement have shown that measuring the state of one particle can instantaneously affect another particle, even if they are separated by vast distances. More intriguingly, the order of measurements sometimes appears to influence outcomes in ways that defy traditional causality. But how can this be? To understand why the reverse paradox is so perplexing, consider a simple everyday situation. You trip and fall, scraping your knee. You think, I tripped and that's why I got hurt. But what if, in some reverse sense, your scraped knee existed first and your fall happened to justify it? It sounds absurd, but it's the kind of thought experiment that challenges our fundamental assumptions about how the world works. Now think about human experiences that seem to hint at reversed causality. Have you ever felt a sense of déjà vu, that eerie feeling that you've lived through a moment before it actually happened? Or perhaps you've experienced a sudden realization, where the answer to a problem comes to you before you've even consciously processed the question. These experiences might not be evidence of reversed causality, but they hint at how our perception of time and sequence can be misleading. Let's take a more concrete example, the act of planning. Imagine you write a list of tasks to accomplish throughout the day. As you check off each task, you feel a sense of completion. But did you complete the task because you planned it, or did the act of writing the plan itself arise because you knew, on some level, that the tasks would be completed? It's a subtle difference, but it blurs the line between cause and effect. Philosophers have long debated the concept of backward causation. One argument suggests that if time were truly symmetrical, there would be no fundamental reason why causes couldn't follow effects. The only reason we perceive time as moving forward is because we are biologically and psychologically wired to experience it that way. Think about how we remember the past but not the future. Our memories are like a trail of breadcrumbs leading back through time, but what if there were beings that remembered the future instead? For them, reversed causality would be entirely natural. They would perceive actions as following their consequences, not the other way around. But what about the implications of the reverse paradox for free will? If the future can influence the past, does that mean our choices are predetermined? If your decision to act is influenced by a future event, are you truly making that decision, or is it being dictated by something that has already occurred in reverse? The reverse paradox doesn't just challenge physics, it challenges our sense of agency. If causes can follow effects, then how do we know our actions are truly our own? Could it be that what we perceive as decisions are merely responses to events that have already been set in motion? In literature and storytelling, the reverse paradox often appears as a plot device. Think of stories where characters receive a message from the future, only to realize that their actions in the present are guided by that very message. The cause and effect loop in these narratives blurs the line between intention and inevitability. Now let's address the resolution to the reverse paradox. The key to resolving this paradox lies in recognizing that causality, as we understand it, is a framework imposed by human perception. In classical physics, causes do indeed precede effects. But in the quantum realm, where particles exist in superpositions and interactions defy linear progression, the concept of reversed causality is not entirely outlandish. One proposed resolution is the idea that causality itself might be a localized phenomenon. On a macro scale, where we live and function, time moves in one direction and causality follows. But on a quantum level, where the rules are more fluid, reversed causality could coexist with traditional causality without creating logical contradictions. But this resolution leaves us with a lingering question. If time itself is not absolute, and if causality can be reversed under certain conditions, does that mean our entire perception of reality is fundamentally flawed? Are we merely interpreting a complex, intertwined system of cause and effect through a narrow, one-way lens? And if we could truly manipulate time, would we be able to change the past by affecting the future? Or would every change we make simply become another link in an unbreakable chain of events, forever intertwined and inseparable, like the fabric of the universe itself? Catch-22 paradox begins in a setting of absurd bureaucracy. Imagine a soldier named John stationed in a war zone. The air is thick with danger, bombs exploding in the distance, and the constant drone of enemy planes circling overhead. John wants to get out. He wants to go home, but there's a catch. The military has a rule, Catch-22. According to this rule, if a soldier is mentally unfit to fly dangerous missions, he can be declared insane and sent home. However, in order to request a discharge for insanity, the soldier must explicitly request it. But the very act of requesting to be discharged is considered a rational act of self-preservation, proving that the soldier is actually sane. Therefore, if John asks to be discharged for being insane, his request is denied because by asking, he demonstrates that he is not insane. The rule creates a perfect loop, a paradox in which every possible action reinforces the impossibility of escaping. No matter what John does, he is trapped by a logic that defies logic. But the paradox doesn't end there. Imagine another scenario. You're trapped in a job you hate. You want to quit, but you can't afford to. Your boss tells you, if you don't like working here, then just quit. But if you quit, you won't have the money to survive, and if you stay, you're trapped in a job that drains the life out of you. You're stuck in a catch-22, a no-win situation where every option loops back on itself, trapping you in a cycle of frustration. Now think about the structure of the catch-22. It's not just a contradiction. It's a self-reinforcing cycle of logic that traps its victim in a loop. The soldier cannot prove he is insane because the very act of trying to prove it demonstrates that he is sane. The worker cannot escape the job because escaping requires money, and earning money requires staying in the job. In every catch-22 scenario, the person caught in the loop is forced to confront the absurdity of the system. The rules are arbitrary, contradictory, and inescapable, yet they are presented as if they are perfectly logical, creating a situation where reason and madness become indistinguishable. Now let's consider a more personal example. Imagine a student named Lisa. She's struggling with her grades and desperately needs a tutor to help her pass her classes. But to afford the tutor, she needs to get a part-time job. However, working the job takes up all her free time, leaving her with no time to study. Without time to study, her grades continue to fall, making her even more in need of a tutor. But without good grades, she can't keep the job. And without the job, she can't afford the tutor. Lisa is trapped in a perfect catch-22. Every possible action leads back to the same problem, a loop with no exit, no solution, no escape. But why does the catch-22 paradox feel so deeply frustrating? It's because the paradox isn't just a logical contradiction, it's a systemic contradiction. The rules themselves are constructed to be unbreakable, reinforcing each other in a way that ensures the trap remains closed. The person caught in the paradox is forced to play by rules that contradict each other, yet are presented as if they are perfectly reasonable. Now consider how the catch-22 paradox plays out in larger systems, governments, corporations, bureaucracies. Imagine a whistleblower who wants to report corruption, but is told that they must go through official channels to do so. But the officials in those channels are the very people the whistleblower is trying to report. If the whistleblower speaks up, they are silenced. If they stay silent, the corruption continues. Or think of someone trying to get a loan to start a business. The bank says, "We can only give you a loan if you can prove you're financially stable." But to become financially stable, the person needs the loan to start the business. Another loop, another trap. But what is the resolution to the catch-22 paradox? The key to resolving the catch-22 paradox lies in recognizing the absurdity of the system itself. The rules are not logically consistent. They are designed to be contradictory, to trap the person in a state of perpetual frustration. The only way to resolve the paradox is to step outside of the system altogether, to reject the rules that create the loop in the first place. For John, the soldier, this means acknowledging that the system is inherently unjust and refusing to play by its rules. For Lisa, the student, it means finding a way to break the cycle, perhaps by seeking help from a mentor, asking for a loan from a friend, or finding a less demanding job. But this raises a deeper question. What if the catch-22 isn't just a bureaucratic trap, but a fundamental aspect of life itself? What if every decision we make is part of a larger system of contradictions, where every choice reinforces the very conditions that created the problem? What if the illusion of choice is just that, an illusion, a carefully constructed trap designed to keep us running in circles, chasing solutions that only deepen the paradox? And if that's the case, then how do we ever escape the loop? How do we break free from a system where every move leads back to the same starting point, where every attempt at escape only tightens the noose? Or is the only way out to refuse to play the game altogether, to step back and say, "No, I won't accept these rules," even if it means accepting the consequences of noncompliance? And if we do that, what kind of freedom do we gain? The freedom to choose, or the freedom to walk away from the very concept of choice itself? The voting booth paradox begins with a seemingly straightforward scenario. You walk into a voting booth, ready to cast your vote in a crucial election. You know the stakes are high, but you also know that your single vote is unlikely to sway the outcome. You stand there, ballot in hand, and a question echoes through your mind: does my vote really matter? Imagine a close election where two candidates are neck and neck. Every vote counts, they say, but statistically speaking, the odds that your individual vote will decide the election are astronomically low. Even in a razor-thin race, the chance that a single vote will tip the scale is almost negligible. So why bother voting at all? This is the essence of the voting booth paradox. It's a paradox that challenges our most basic assumptions about civic duty, collective action, and rational decision-making. If your vote is so unlikely to make a difference, then rationally, it would seem pointless to vote. But if everyone thinks this way, no one votes, and the entire system collapses. Now, imagine this paradox playing out on a larger scale. You're in a city with 1 million registered voters. Each voter thinks, my single vote won't change the outcome. And technically, they're right. The probability of one vote deciding the outcome is infinitesimally small. But if everyone thinks this way, voter turnout plummets and the election becomes a farce, decided by a tiny minority while the majority stays home, convinced that their votes don't matter. But the paradox doesn't end there. Imagine a voter named Sarah. Sarah knows that her vote is unlikely to be decisive, but she votes anyway, not because she thinks she will personally swing the election, but because she believes in the collective power of voting. If everyone acts as Sarah does, the paradox dissolves. But if everyone thinks someone else will vote, the paradox deepens. Now consider a different scenario. Imagine an election where a wealthy corporation can buy thousands of votes, effectively swinging the outcome in their favor. You stand in the voting booth, aware that your single vote is a drop in the ocean compared to the tidal wave of influence wielded by the corporation. Does your vote matter now? In this version of the paradox, the question is not just about the statistical impact of a single vote, but about the power dynamics at play. If certain entities can exert disproportionate influence, does that not render individual votes effectively meaningless? And if so, does the act of voting become a symbolic gesture rather than a genuine exercise of power? But let's shift perspective. Imagine a close election decided by just one vote. It has happened before in local races, in congressional districts, in state referendums. In these cases, the paradox is shattered by the undeniable impact of a single vote. But these cases are rare, statistical outliers. Most elections are not decided by one vote, but by thousands, even millions. Now, consider a psychological dimension of the paradox. Imagine a voter named Tom. Tom knows his vote is unlikely to matter, so he stays home. But when the results are announced, his preferred candidate loses by a single vote. Tom feels a crushing sense of guilt, convinced that his decision not to vote caused the loss. But did it? After all, if Tom had voted, would the outcome really have changed? And what about all the other non-voters who also thought their votes wouldn't matter? This guilt complex reveals another layer of the paradox, the tension between individual responsibility and collective action. If everyone thinks, my vote doesn't matter, the collective impact is profound. But if everyone thinks, my vote could matter, the system functions as intended. Now let's consider how the voting booth paradox plays out in a world of increasing voter apathy. Imagine a country where voter turnout is at an all-time low. Politicians exploit this by targeting only the most likely voters, a small, predictable subset of the electorate. Meanwhile, the majority remains disengaged, convinced that their votes are meaningless. The paradox becomes a self-fulfilling prophecy as apathy breeds disillusionment and disillusionment breeds apathy. But what is the resolution to the voting booth paradox? The key lies in reframing the act of voting. Instead of viewing voting as a purely individual act with negligible impact, we can view it as a collective action problem. Individually, each vote may seem meaningless, but collectively, the power of voting is immense. It's like a single drop of water in a bucket, insignificant on its own, but when combined with millions of others, it fills the bucket to overflowing. But this resolution raises a deeper question. If voting is only meaningful when viewed collectively, does that mean our individual choices are illusions? Are we merely cogs in a larger machine, our personal agency subsumed by the collective will? And if so, what does that say about democracy itself? Is it truly a system where every vote counts, or is it a system where every vote is equally powerless, a symbolic gesture in a vast sea of statistical noise? Now let's address the core of the paradox one more time. Imagine standing in the voting booth, ballot in hand. You stare at the list of candidates, aware that your single vote is unlikely to change the outcome. You could walk away, convinced that your vote doesn't matter. Or you could cast your vote anyway, not because you believe it will decide the election, but because you believe in the collective power of millions of seemingly insignificant votes. In that moment, you face the heart of the paradox, the tension between individual insignificance and collective power. You cast your vote not because it will decide the election, but because if everyone thinks their vote doesn't matter, the system collapses. And if everyone thinks their vote does matter, the system works as intended. But this leaves us with a haunting question. If the value of a vote is only realized collectively, then what is the true nature of democracy? Is it a system that empowers individuals, or is it a system that renders individuals powerless, masking the illusion of choice behind the spectacle of the ballot box? And if our votes are just drops in the ocean, then how much power do we really hold? And how much of that power is just an illusion, a comforting lie we tell ourselves to keep believing in a system that may not be as democratic as it seems? Simpson's paradox begins with a simple observation. Sometimes, when you look at data in separate groups, you see one trend, but when you combine those groups, the trend reverses completely. Imagine you're at a hospital evaluating two different treatments for a deadly illness. The data is clear. Treatment A has a higher survival rate for men and a higher survival rate for women. But when you look at the overall data, combining both men and women, suddenly, treatment B appears to have the higher survival rate. How can that be? This is the essence of Simpson's paradox, a statistical phenomenon that reveals how the interpretation of data can shift dramatically depending on how the data is grouped or aggregated. It's a paradox that challenges our fundamental assumptions about cause and effect, making us question what we think we know about the relationships between variables. Let's break it down. Imagine two hospitals, each treating a large number of patients. Hospital X uses treatment A, and Hospital Y uses treatment B. The data for men shows that treatment A has a 75% survival rate, while treatment B has a 60% survival rate. The data for women shows that treatment A has an 80% survival rate, while treatment B has a 70% survival rate. Clearly, treatment A appears to be more effective for both men and women, but when you combine the data for both genders, the overall survival rate for treatment B is suddenly higher. How is that possible? The answer lies in the way the data is distributed. If Hospital X treated more severe cases and Hospital Y treated milder cases, the overall numbers could be skewed. For instance, if most of the severe cases received treatment A and most of the mild cases received treatment B, the combined data would make treatment B appear more effective, even though it was actually less effective in each subgroup. Now, let's consider a more relatable example. Imagine a college is evaluating two different teaching methods, Method A and Method B. The data shows that Method A improves grades for both freshmen and seniors. But when the data is combined, Method B appears to have the higher overall improvement. How can a method be more effective for both freshmen and seniors, but less effective overall? Again, the answer is in the distribution. Suppose Method A was primarily used for freshmen, who started with much lower grades, while Method B was primarily used for seniors, who started with higher grades. When the data is combined, the overall average may be skewed by the differing baseline grades, making it seem like Method B is more effective. But why does Simpson's paradox feel so counterintuitive? The paradox arises because we intuitively expect data to tell a consistent story. If one treatment is better for men and better for women, we assume it should also be better overall. But when data is aggregated across groups with different baseline rates, the combined result can tell a completely different story. Now, let's explore the implications of Simpson's paradox in the real world. Imagine a city evaluating two different policing strategies to reduce crime. Strategy A is more effective in high-crime areas, and Strategy B is more effective in low-crime areas. The data shows that Strategy A reduces crime more effectively in both types of neighborhoods. But when the data is combined, Strategy B appears to be more effective overall. How can that be? Suppose most of the crimes occur in high-crime areas, where Strategy A is applied. Meanwhile, the low-crime areas, where Strategy B is applied, have fewer crimes overall. When the data is combined, the overall crime reduction appears greater in the areas using Strategy B, even though Strategy A was more effective in each specific area. This is the insidious nature of Simpson's paradox. It reveals how data can be manipulated, intentionally or unintentionally, by the way it is grouped, aggregated, or presented. In politics, marketing, and scientific research, this paradox can be exploited to create misleading conclusions that appear logical on the surface but fall apart under closer scrutiny. Now, let's consider a historical example. In the 1970s, the University of California at Berkeley was accused of gender discrimination in its graduate school admissions. The data showed that men were admitted at a higher rate than women, but when the data was broken down by department, a surprising pattern emerged. In most departments, women actually had higher acceptance rates than men. How could the overall data show discrimination against women when most departments were favoring female applicants? The answer was Simpson's paradox. Women had applied in higher numbers to more competitive departments, such as humanities and social sciences, where acceptance rates were lower overall. Meanwhile, men had applied in greater numbers to less competitive departments, such as engineering and natural sciences, where acceptance rates were higher. The overall data masked the fact that, within each department, women were actually being admitted at higher rates. Now, let's address the resolution to Simpson's paradox. The key to resolving the paradox lies in recognizing that data aggregation can obscure important patterns. The paradox is not a flaw in the data itself, but in the way the data is presented and interpreted. To resolve the paradox, we must consider the data at both the group level and the overall level, identifying potential confounding variables that could be influencing the results. But this resolution raises a deeper question. If data can so easily mislead us, how much of what we believe about cause and effect is based on flawed interpretations? How many policy decisions, scientific conclusions, and personal beliefs are shaped by aggregated data that obscures the true relationships between variables? And if the truth can be hidden in plain sight, masked by the very data that is supposed to reveal it, then how much can we really trust the numbers? And how often are we falling victim to paradoxes we don't even realize are there? Buridan's bridge paradox begins with a confrontation. Imagine you're standing at the edge of a bridge, and on the other side stands a guard named Buridan. Buridan blocks the bridge, his arms crossed, eyes locked onto yours. He speaks in a calm but firm tone. "If you tell me the truth, I will let you pass, but if you lie, I will throw you into the river." You pause, considering his words carefully. The bridge is the only way to cross the river, and you need to get to the other side. But now, you are caught in a paradox, a logical trap that seems to have no escape. You think to yourself, if I say, "You will throw me into the river," then what happens? If you're telling the truth, then Buridan will let you pass. But if he lets you pass, then your statement was false, and he should have thrown you into the river. But if your statement was false, then he should have thrown you into the river, making it true. It's a perfect loop, a logical trap that twists back onto itself, where every possible outcome contradicts itself. Buridan's bridge paradox is a classic example of self-referential logic, a statement that simultaneously asserts and denies its own truth. Now let's break it down further. Imagine you decide to say, "You will not throw me into the river." If Buridan believes you are telling the truth, he will let you pass. But if he lets you pass, then your statement was true, and he did not throw you into the river. That seems straightforward. But what if he thinks you are lying? If he thinks you are lying, then your statement, "You will not throw me into the river," is false, and he must throw you into the river. But by throwing you into the river, he makes your statement true, which means you weren't lying. This creates a paradox of action, a loop where Buridan's response becomes impossible to resolve without contradicting itself. But let's take it a step further. Imagine that instead of a bridge, Buridan is guarding a door. Behind the door is a treasure chest, and the rule is the same. If you tell the truth, you may enter. If you lie, you will be thrown into the river. You step forward and say, "You will throw me into the river." Now Buridan is faced with a dilemma. If he lets you enter, then your statement was false, and he should have thrown you into the river. But if he throws you into the river, then your statement was true, and he should have let you enter. It's a logical trap where every possible outcome contradicts itself, creating an endless loop of indecision. But why is this paradox so difficult to resolve? The problem lies in the self-referential nature of the statement. Your statement, "You will throw me into the river," is not just a prediction, it's a statement about Buridan's future action. It forces Buridan to consider not just what you said, but how his response will retroactively alter the truth value of your statement. In other words, the paradox forces Buridan to act in a way that simultaneously confirms and denies the truth of the statement, creating a loop that cannot be logically resolved. Now let's apply this paradox to a more familiar setting. Imagine you're in a courtroom standing before a judge who says, "If you tell the truth, you will be set free. If you lie, you will be jailed." You respond, "You will jail me." Now the judge is caught in the same paradox. If he sets you free, then your statement was false and you should be jailed. But if he jails you, then your statement was true and you should have been set free. The courtroom descends into chaos as the logical loop closes in on itself, creating a paradox with no exit. But what is the resolution to Buridan's bridge paradox? The key to resolving the paradox lies in rejecting the premise that the guard Buridan must act based solely on the truth or falsehood of the statement. In reality, Buridan could simply refuse to engage with the paradox, choosing to act independently of the logical trap you've set for him. He could say, "I don't care if your statement is true or false, I will act based on other criteria." Alternatively, Buridan could declare the statement to be indeterminate, neither true nor false, thus escaping the logical loop by refusing to play by its rules. But this resolution raises a deeper question. What if every rule, every law, every system of logic we rely on is itself a potential paradox, a trap waiting to spring closed around us? Imagine a society where every law operates like Buridan's bridge, where every rule is a logical loop that contradicts itself, trapping citizens in a maze of indecision and contradiction. In such a society, how could justice ever be served? How could truth ever be determined? And if every rule is a potential paradox, then how do we know that the laws we follow are not themselves paradoxical? How do we escape a system where every choice leads to a contradiction, where every statement loops back on itself, endlessly folding, collapsing, and reforming? Into another paradox. Or perhaps the only way to resolve the paradox is to step off the bridge, walk away from the door, and refuse to play the game. But in doing so, do we not create another paradox, the paradox of refusal, the paradox of choosing to do nothing in the face of a system that demands action? And if we choose to do nothing, then what have we really escaped, the paradox or the illusion of choice itself? Imagine you're standing in the middle of a crowded city square. Around you, people are shouting their opinions, each one convinced that they know what's best for everyone else. Some want a park built where the old factory stands, others want a shopping mall, still others want the space converted into housing for the homeless. Each person has their own preferences, their own priorities, their own vision of what the city should be. Now you're put in charge of making the final decision, but you can't just pick what you want. You have to make a decision that reflects the collective will of the entire city, every opinion, every preference, every competing interest. You decide to hold a vote. Everyone writes down their first choice, their second choice, and their third choice. You gather up the votes, sort them, and try to come up with a fair way to rank the options. But as you go through the ballots, something becomes painfully clear. The more you try to make everyone happy, the more impossible the task becomes. You try ranking the choices by majority rule, but that leads to contradictions. One group of voters ranks the park first, the mall second, and housing third. Another group ranks the mall first, housing second, and the park third. And yet another group ranks housing first, the park second, and the mall third. Each ranking conflicts with the others, and there is no way to create a fair and consistent ranking that satisfies everyone. The contradictions pile up, and no matter how you arrange the preferences, someone is always left feeling like their vote didn't matter. This is the essence of Arrow's Impossibility Theorem, a paradox that reveals the fundamental flaws in voting systems, showing that no method of voting can simultaneously meet all the criteria for a fair and democratic decision-making process. Now let's break it down further. Imagine that instead of 3 options, there are 5. Now, the number of possible rankings multiplies exponentially. Each voter ranks the options differently, and the number of possible conflicts increases. You try to implement a system where the most popular choice always wins, but then you realize that what's most popular isn't always what's most preferred. You try a method where the least popular option is eliminated first, but then you realize that eliminating the least popular option changes the overall ranking order, creating new contradictions. Every time you think you've found a fair system, a new conflict emerges. The paradox tightens its grip, revealing that no voting method can resolve the contradictions without violating one of Arrow's criteria. Now let's go deeper. Imagine that instead of a city council, you are part of a company's board of directors. The board is voting on whether to invest in a new product, expand the current product line, or cut costs and downsize. Each board member ranks the options according to what they think is best for the company, but their rankings are all different. You decide to use a ranked voting system, but the same contradictions arise. The more you try to balance everyone's preferences, the more the rankings contradict each other. If you prioritize the majority, you undermine the minority. If you prioritize the minority, you ignore the majority. The paradox is everywhere, woven into the very fabric of collective decision-making. No matter how you structure the vote, the contradictions remain unresolved and unresolvable. Now let's take it even further. Imagine that instead of a company, you are a leader of a nation. You are trying to decide how to allocate the country's resources, healthcare, education, infrastructure. Each group of citizens has different priorities, different needs, different preferences. You decide to hold a nationwide vote, asking everyone to rank their top 3 priorities. The votes pour in and the contradictions pile up. The wealthiest citizens prioritize tax cuts and economic growth. The middle class prioritizes affordable housing and job security. The poorest citizens prioritize food assistance and healthcare access. You try to reconcile these rankings, but the more you try to please everyone, the more dissatisfied everyone becomes. Each ranking conflicts with the others, and there is no way to create a single, consistent ordering that accurately reflects the collective will of the people. Now the paradox reveals its true nature. Arrow's impossibility theorem isn't just a quirk of voting systems. It's a fundamental flaw in collective decision-making itself. It reveals that no matter how much data you collect, no matter how many votes you count, no matter how many rankings you sort, the contradictions remain. The paradox teaches us that democracy itself is inherently flawed, that the very act of trying to aggregate individual preferences into a collective decision creates logical contradictions that cannot be resolved. But what is the resolution to Arrow's impossibility? Theorem. The answer lies in recognizing that there is no perfect voting system. There is no way to aggregate individual preferences into a single, fair ranking without encountering contradictions. The paradox is not meant to be solved. It is meant to be acknowledged, accepted, and worked around. But this raises a deeper question. If democracy is inherently flawed, then what does that say about the decisions we make every day? If every voting system is doomed to failure in some way, then how can we ever trust the results of an election? How can we ever be sure that the will of the people is truly being reflected in the final decision? And if every decision-making system is inherently flawed, then what does that say about us? Are we doomed to live in a world where our preferences are always misrepresented, where our voices are always drowned out, where our votes are always counted but never truly heard? And if the only way to resolve the paradox is to accept that no voting system can be perfect, then what does that say about the nature of choice itself? Is choice an illusion, a comforting lie we tell ourselves to feel in control, even when the outcome is predetermined by the contradictions in our own preferences? And if that's the case, then what if the real paradox isn't the voting system, but the belief that we can ever resolve the contradictions in our own desires, that we can ever create a system that perfectly represents our collective will, that we can ever find a way to make everyone happy, even when our preferences are pulling us in opposite directions? Maybe the real paradox isn't in the voting booth, but in the human heart, a place where our deepest desires are constantly at odds with each other, spinning endlessly in a cycle of contradiction, forever trying to resolve the unresolvable. Protagoras versus Euathlus paradox begins in a courtroom. Imagine a teacher and his student standing before a judge, both determined to win a case that seems impossible to resolve. The teacher, Protagoras, is a brilliant and cunning lawyer. The student, Euathlus, is ambitious but still learning the ropes. Years earlier, Euathlus had approached Protagoras with a deal. Protagoras agreed to teach Euathlus the art of law, but with one condition: Euathlus would only have to pay for his lessons after he won his first case. Euathlus agreed, confident in his abilities. But as time passed, Euathlus completed his training and began practicing law. Yet, he deliberately avoided taking on any cases, refusing to pay Protagoras under the logic that he had not yet won his first case. Frustrated, Protagoras decided to sue Euathlus, demanding payment for the lessons, and this is where the paradox begins. Imagine the scene in the courtroom. Protagoras steps forward, a confident smirk on his face. He addresses the judge, laying out his argument. If I win this case, Euathlus must pay me according to the court's ruling. But if I lose, Euathlus will have won his first case and will then owe me payment under our original agreement. Therefore, regardless of the outcome, Euathlus must pay me. The judge nods, finding the logic compelling, but then Euathlus steps forward, a determined look in his eyes. He counters. If I win this case, the court has ruled that I do not have to pay Protagoras as he has lost. But if I lose, then I still have not won my first case, and therefore, under our original agreement, I do not owe him any payment. Therefore, regardless of the outcome, I do not have to pay Protagoras. The judge is stunned. Both arguments seem airtight, yet they directly contradict each other. If Protagoras wins, he loses. If Euathlus loses, he wins. The paradox has created a perfect loop, a logical trap where every possible outcome leads to a contradiction. But how can this be? The essence of the Protagoras versus Euathlus paradox lies in its self-referential nature. Each argument is contingent upon the outcome of the other, creating a loop where each side's logic undermines the other's. It's a paradox of circular reasoning, where each statement validates itself by invalidating the other. Now let's break it down further. Protagoras' argument is based on contractual logic. He asserts that payment is due whether he wins or loses because the contract itself stipulates that Euathlus must pay upon winning his first case, and winning the current case would qualify as such. Euathlus' argument, however, is based on judicial logic. He asserts that payment is not due because the outcome of the current case will determine his obligation. If he loses, he still has not won his first case. If he wins, the court has ruled that he owes nothing. The paradox emerges because both arguments rely on the outcome of the case to validate themselves. Protagoras claims that winning the case secures his payment, but Euathlus claims that losing the case prevents payment. Each argument is logically sound in isolation, but when combined, they cancel each other out. But let's take it a step further. Imagine that the judge is now tasked with rendering a verdict. If he rules in favor of Protagoras, he must simultaneously rule that Euathlus has won his first case, thereby triggering the contract and making Euathlus liable for payment. But in doing so, he also validates Euathlus' argument that he has not yet won his first case, which negates the contract and invalidates the payment. On the other hand, if the judge rules in favor of Euathlus, he must simultaneously rule that Euathlus has not yet won a case, thereby upholding the contract's condition that payment is not yet due. But in doing so, he also invalidates Protagoras' argument that winning the case entitles him to payment, creating a logical contradiction. Now consider the implications of this paradox in the broader context of law and contracts. Imagine a contract where payment is contingent upon the occurrence of a specific event. But what if that event is itself contingent upon the contract being fulfilled? The contract creates a loop, a logical deadlock where each condition negates the other, making it impossible to resolve without contradicting itself. Or think of a legal dispute where the outcome of the case determines the validity of the very contract being contested. If the contract is valid, the case proceeds. But if the case proceeds, the contract is invalidated. This is the essence of circular reasoning in legal disputes, a loop where the outcome and the premise become indistinguishable, each feeding back into the other without resolution. But what is the resolution to the Protagoras versus Euathlus paradox? One proposed resolution involves reframing the agreement. Instead of interpreting the contract as contingent upon winning the first case, we interpret it as contingent upon the completion of legal training. In other words, the contract is fulfilled not by winning a case, but by completing the lessons. Thus, Protagoras is entitled to payment regardless of the outcome of the current case. Another resolution involves rejecting the paradox altogether, asserting that the contract itself is void due to its contradictory nature. If a contract contains a self-referential loop that renders it logically inconsistent, then it cannot be legally enforced, and the dispute dissolves. But this raises a deeper question. If legal contracts can be rendered unenforceable by paradoxes, How many other agreements, rules, and systems are similarly flawed? How many other logical loops are hiding within the frameworks we rely upon, waiting to trap us in a cycle of self-referential contradictions? And if logic itself can be turned against us in this way, how do we ever escape the loop? How do we resolve a paradox where every solution creates another problem, where every answer leads back to the same question, looping endlessly like a serpent swallowing its own tail? Or is the only true resolution to recognize that the paradox itself is the answer, that life, law, and logic are all just endless cycles of contradiction, and that the only way to win is to stop playing the game? The paradox of envy begins with a simple but unsettling question. If you could swap your life with someone else's, would you? Imagine a room full of people, each holding a piece of paper with a number on it. The number represents their total wealth, happiness, and life satisfaction. You stand in the center of the room, holding your own piece of paper, looking around at everyone else. Some numbers are higher than yours, some are lower. Now the host of the room steps forward and announces, "You may trade your number with anyone in this room, but once you trade, you cannot trade back. Choose carefully." You look around the room, eyeing the people holding the higher numbers. You feel the pang of envy, the desire to trade up to get more. But as you watch, you notice something strange. Everyone else is hesitating too. They're all looking around, sizing each other up, considering their options. Why aren't they trading? This is the essence of the paradox of envy. It's the realization that while you might envy someone else's life, they might be envying yours. And if everyone is envious of someone else, then no one is truly content. Everyone is trapped in a loop of dissatisfaction, convinced that someone else has it better, while simultaneously fearing that they might end up worse off by trading places. Now let's break it down further. Imagine two people, Alex and Jamie. Alex is wealthy, successful, and admired by everyone. Jamie is struggling financially but has a loving family and close friends. Alex envies Jamie's strong social connections, feeling lonely despite his wealth. Jamie envies Alex's financial stability, feeling insecure despite his strong relationships. If given the option to trade lives, both hesitate. Alex fears losing his wealth and status, even though he craves connection. Jamie fears losing his close relationships, even though he craves financial security. Each is trapped in a cycle of wanting what the other has, but being too afraid to give up what they already possess. This is the paradox. The very things that people envy in others are the things they are unwilling to sacrifice in themselves. Now let's take it a step further. Imagine a society where everyone is allowed to trade lives once a year. Each person can choose someone whose life they envy and take their place. But there's a catch. You don't get to see the full picture of the other person's life. You only see the part they display to the world, their wealth, their social status, their appearance. You don't see their hidden struggles, their fears, their regrets. You don't see the parts of their life they keep hidden behind closed doors. Now imagine that you trade places with someone you envy. You step into their life feeling excited, powerful, invincible. But as the days go by, you start to see the cracks. You realize that the person you envied was dealing with crushing debt, a toxic relationship, or a chronic illness. You start to regret the trade, wishing you could go back to your old life. But the trade is permanent. You're stuck. The paradox of envy reveals a fundamental flaw in how we perceive others. We compare our internal struggles with others' external appearances, assuming that what they show to the world is the whole truth, but it rarely is. The truth is always messier, more complicated, more painful than it appears on the surface. Now consider how the paradox of envy plays out in the age of social media. Every day we scroll through carefully curated images of other people's lives, vacation photos, luxury cars, expensive dinners. We see the highlight reel, not the behind-the-scenes footage. We compare our everyday struggles with their curated perfection and feel inadequate, envious, resentful. But what if the people we envy are just as envious of us? What if they too are looking at our lives, our successes, our relationships, and feeling the same pangs of envy we feel toward them? The paradox deepens. Imagine a world where everyone is constantly trading lives, hoping to find happiness, only to discover that every life has its own set of hidden struggles. The wealthy man trades places with the artist, seeking creative fulfillment, only to discover the artist is struggling with poverty. The artist trades places with the wealthy man, seeking financial stability, only to discover that the man is lonely, disconnected, and drowning in pressure. No one is content because everyone is convinced that someone else has it better, but no one actually does. The paradox loops endlessly, a cycle of envy that feeds itself, consuming everyone in its path. Now, let's address the resolution to the paradox of envy. The resolution lies in the realization that the act of envying someone else's life is inherently flawed. When we envy, we compare our entire reality, the good, the bad, the ugly, with a selective, curated snapshot of someone else's life. We see only the parts they want to show us, not the whole picture. The key to breaking the cycle of envy is to recognize that every life is complex, multifaceted, and filled with both blessings and burdens. No life is objectively better or worse than another. Every life comes with its own set of challenges and rewards, and the parts we envy in others are often balanced by struggles we do not see. But this resolution raises a deeper question. If every life is equally flawed, then what does that say about the nature of envy itself? Is envy a natural human response, or is it a product of our own selective perception, a cognitive illusion that blinds us to the full reality of others' lives? And if the lives we envy are just as imperfect as our own, then what are we really chasing when we feel envious? Are we seeking a life without struggle, a life that doesn't exist, or are we simply seeking a distraction from our own pain, a way to avoid facing the parts of our own lives we'd rather not confront? And if so, then what if the real paradox of envy isn't that we want what others have, but that we don't even want what we already have? What if the real paradox is that we are all too busy envying others to appreciate the life we're already living, the life we're too afraid to trade away, even if given the chance? Imagine you're sitting in a crowded cafe, scrolling through your social media feed. Photos of exotic vacations, fancy dinners, new cars, and smiling faces flood your screen. You feel a tightening in your chest, a sense of unease that you can't quite shake. You look at your own life, the empty cup of coffee in front of you, the unfinished work piling up, the same four walls you see every day, and you can't help but feel envious. You know that envy is a destructive emotion, that it doesn't change your circumstances or make you any happier. But you can't stop scrolling, you can't stop comparing, you can't stop feeling like everyone else is living a better life than you. But then a thought crosses your mind. What if the people you envy are also feeling envy themselves? What if the friend posting vacation photos is envying someone who is richer? What if the person driving the luxury car is envying someone who has more freedom? What if the person smiling in that perfect couple's selfie is envying someone who is single and carefree? Suddenly you realize that envy is a cycle, a loop that never ends. No matter what you have, there is always someone who has more, and no matter what you lack, there is always someone who envies what you do have. The paradox emerges. Envy is a feeling that makes you feel less than others, even when the very people you envy might be envying you in return. Now let's break it down further. Imagine two neighbors living side by side. The first neighbor, Mark, is a successful businessman. He has a big house, a luxury car, and plenty of money. But every day he watches his neighbor, Tom, through the window. Tom is a writer who spends his days at home working on his novel. He has no money, no fancy possessions, but he has time to write, time to relax, time to think. Mark envies Tom's freedom. He wishes he could spend his days writing instead of working. Meanwhile, Tom envies Mark's wealth. He wishes he had the money to travel, to buy new clothes, to live comfortably. Each man is trapped in a loop of envy, each one convinced that the other has the better life. But the paradox deepens. One day, Mark loses his job. The business collapses and the luxury car is repossessed. He's forced to downsize, to move into a smaller house, to live on a tight budget. But now he has time to write, time to relax, time to think. Tom, on the other hand, finally sells his novel. It becomes a bestseller, and suddenly he is flooded with money, with opportunities, with attention. But now he has no time. He is overwhelmed with meetings, interviews, deadlines. He is stressed, exhausted, and longing for the quiet days when he could sit by the window and watch the world go by. Now both men have switched places. Mark envies Tom's success. Tom envies Mark's freedom. The cycle of envy continues, looping endlessly, spinning both men in circles of desire and dissatisfaction. Now let's go deeper. Imagine that instead of neighbors, we are dealing with two countries. Country A is wealthy but politically unstable. Its citizens have money but live in fear of corruption and crime. Country B is poor but peaceful. Its citizens are safe but struggle to make ends meet. Country A envies Country B's peace and stability. Country B envies Country A's wealth and opportunity. The leaders of each country hold secret meetings, trying to figure out how to obtain what the other has. They plot, they plan, they strategize, each one trying to steal what the other possesses. But in the end, nothing changes. Each country remains trapped in its own cycle of envy, unable to see that what they already have is what the other truly wants. Now let's take it even further. Imagine that instead of countries, we are dealing with two versions of yourself. The first version of you is the person you are right now, the person with flaws, with failures, with insecurities. The second version of you is the idealized version, the person you wish you could be, the person who is confident, successful, happy. You spend your days envying the idealized version of yourself, convinced that if you could just become that person, you would finally be happy. But here's the paradox: the idealized version of yourself is also envying you. That version of you is looking back at the present you, wishing for the simplicity, the freedom, the sense of possibility that comes with not having everything figured out. The idealized you is trapped by their own success, burdened by their own perfection, longing for the days when life was simpler, when mistakes were still possible, when there was still room to grow. Now the paradox tightens. You are envying yourself, but the self you envy is also envying you. The cycle loops endlessly, and no matter which version of yourself you become, the envy remains. But what is the resolution to the paradox of envy? The key lies in recognizing that envy is a distortion of reality. It is the act of comparing our inside to someone else's outside, of measuring your flaws against someone else's highlights. It is a game you can never win, because the more you play, the more you lose. But this raises a deeper question. If envy is an illusion, then what are we really chasing? Are we chasing happiness, or are we chasing the illusion of happiness? Are we chasing contentment, or are we chasing the illusion of contentment? And if the people we envy are also envying us, then what does that say about the nature of desire itself? Is desire just a reflection of what we think we lack, even when what we think we lack is actually what others see in us? And if that's the case, then what if the true resolution to the paradox of envy isn't to eliminate envy, but to see through it? To recognize that the things we envy are often illusions, projections, masks that hide the very same insecurities we are trying to escape. And if we can see through the illusion of envy, then what happens to the cycle? Does it break, does it dissolve, or does it simply continue, spinning endlessly in circles, a loop of desire that can never be resolved, a paradox that can never be escaped? And as you sit in that cafe, staring at the screen, scrolling through images of lives that seem more perfect than your own, you can't help but wonder. If the people we envy are also envying us, then what are we really looking at? Are we looking at them, or are we just looking at ourselves, reflected back in the glass of our own desires? And if envy is just a mirror, showing us what we think we lack, then what happens when we finally stop looking? What happens when we turn away from the screen, close our eyes, and realize that what we were searching for out there was inside us all along? Imagine you're at a party, and someone casually mentions that they know a family with 2 children. They tell you that one of those children is a boy. Then they ask you, what do you think the probability is that the other child is also a boy? Your first instinct might be to say 50%. After all, there are only 2 possible genders, boy or girl, so it seems logical to think that if one child is a boy, the other has an equal chance of being either a boy or a girl. But as with many things in probability, what seems logical at first glance isn't always correct. Let's slow down and really think about what we've been told. We know that the family has 2 children and that one of them is a boy, but we don't know which child is the boy. We don't know if it's the older child or the younger child. That lack of specific information is the key to this paradox. Let's break down the possible combinations of 2 children in a family. The first possibility is that both children are boys. The second possibility is that the older child is a boy and the younger child is a girl. The third possibility is that the older child is a girl and the younger child is a boy. The fourth possibility is that both children are girls. But we were told that at least one of the children is a boy. That information allows us to eliminate the scenario where both children are girls. We are left with 3 possible scenarios. The first scenario is that the older child is a boy and the younger child is also a boy. The second scenario is that the older child is a boy and the younger child is a girl. The third scenario is that the older child is a girl and the younger child is a boy. Now, out of these 3 scenarios, only one of them has 2 boys. The other two scenarios each have one boy and one girl. This means that the probability of both children being boys is 1 out of 3, or approximately 33%. Now let's adjust the question slightly. Imagine that instead of saying, one of the children is a boy, the person tells you, the older child is a boy. This time we have more specific information. We are no longer considering the family as a whole. We are focusing on the younger child specifically. In this version of the question, we only have two possibilities to consider. The first possibility is that the younger child is a boy. The second possibility is that the younger child is a girl. Since we know the older child is definitely a boy, the probability of both children being boys is now 50%. This subtle shift in wording completely changes the probability. It highlights how crucial it is to pay attention to how information is framed. In the first version of the question, we were given general information about one of the children. In the second version, we were given specific information about a particular child. That small difference changes the way we calculate the probability. Now let's complicate the question even further. Imagine that instead of saying, one of the children is a boy, the person says, one of the children is a boy born on a Tuesday. Now we have even more specific information. Not only are we told the gender, but we're also given a day of the week. This extra detail makes the probability calculation even more complex. Now, we have to consider each child's gender as well as the day of the week. The number of possible combinations grows exponentially. We need to account for each gender on each day of the week, making the problem far more complicated. For example, if we consider one child being a boy born on a Tuesday, we need to consider the other child being a boy or a girl born on any of the other days of the week. The number of possible combinations multiplies dramatically, and the probability of both children being boys changes once again. This version of the paradox is a powerful reminder of how easily probability can become convoluted when additional information is introduced. It also underscores how critical it is to pay attention to the specific framing of a question, as even the slightest change in wording can lead to dramatically different interpretations and outcomes. But let's step back and consider why this paradox is so perplexing. The boy or girl paradox taps into a deeper cognitive bias known as the representativeness heuristic. Our brains are wired to make quick, intuitive judgments based on surface-level similarities. In this case, we instinctively compare the probability of one child being a boy to the probability of the other child being a boy, treating them as independent events. But they are not independent. The presence of one boy in the family changes the context of the question. It alters the set of possible outcomes and therefore the probability distribution. This subtle shift in perspective is what makes the paradox feel so counterintuitive. Now let's bring this concept into the real world. Imagine a detective investigating a crime involving two suspects. The detective is told that one of the suspects is left-handed. What is the probability that the other suspect is also left-handed? This scenario mirrors the structure of the boy or girl paradox. If the detective focuses solely on the probability of any individual being left-handed, he might miss the broader implications of how the information is framed. Or consider how the paradox plays out in marketing. Suppose a company is analyzing customer data and discovers that one of its top 2 clients made a purchase on a Wednesday. What is the probability that the other client also made a purchase on a Wednesday? The framing of the question matters. Are we asking about a specific client, or are we considering both clients as a group? The structure of the question determines the probability calculation, just as it does in the boy or girl paradox. Ultimately, the boy or girl paradox is more than just a quirky brain teaser. It's a profound exploration of how easily our intuitions can be led astray by framing effects, cognitive biases, and the complexities of probability theory. It teaches us that even the simplest questions can have hidden layers of complexity, and that the way we frame information can dramatically alter the answers we get. And if the framing of a single question can so profoundly alter our perception of reality, then how much of what we believe to be true is merely a function of how the question was asked? How often do we mistake our intuitions for truths, only to discover that the answers were never as straightforward as they seemed? Imagine you're sitting alone in a prison cell, awaiting your execution. You've been told that you will be executed sometime next week, but the exact day will be a surprise. You won't know the day of your execution until the guards come to get you. You spend your days pacing the cold, gray floor, replaying the warden's words in your mind. You will not know the day of your execution until it happens. At first, the words seem straightforward, but as the days drag on, the meaning begins to twist in your mind. You start to reason through it, trying to deduce the day of your execution. You tell yourself, if I haven't been executed by Friday night, then it must happen on Saturday. But if I know it will happen on Saturday, then it won't be a surprise. Therefore, it can't happen on Saturday. You feel a chill run down your spine as you realize that if the execution can't happen on Saturday, then Friday becomes the last possible day. But now, Friday is predictable too. If you're still alive by Thursday night, then the execution must be on Friday. But that wouldn't be a surprise either. Your mind races, spiraling through the days of the week. If it can't be Saturday or Friday, then Thursday becomes the last possible day. But by the same logic, Thursday becomes predictable too. The paradox tightens around you like a noose, each day collapsing in on itself, eliminating the possibility of a surprise. And yet, the warden's words remain, you will not know the day until it happens. This is the essence of the prisoner's paradox, also known as the unexpected hanging paradox. It's a paradox of logic and self-reference, a puzzle that creates a loop of contradictory reasoning. No matter how you think it through, the logic collapses under its own weight, leaving you trapped in a cycle of uncertainty. Now let's step back and break it down. The paradox begins with a statement that is both simple and deceptively complex. You will be executed on a day you do not expect. The prisoner tries to reason through it by working backward from the last possible day. But by doing so, he transforms each day into a predictable outcome, thereby contradicting the original statement that the execution will be a surprise. The paradox hinges on the interplay between knowledge and uncertainty. The prisoner is trying to use logic to predict the unpredictable. He is attempting to eliminate surprise by reasoning through every possible outcome, but in doing so, he inadvertently destroys the very premise of the warden's statement that the day will be unexpected. Now let's take the paradox further. Imagine a different scenario. You're not a prisoner, but a student taking a difficult course. The professor announces that there will be a surprise quiz next week. You think to yourself, if the quiz doesn't happen by Friday, then it must be on Friday, but if I expect it on Friday, it can't be a surprise. Now you reason backward through each day of the week, just like the prisoner. But as each day passes without a quiz, you become more and more convinced that the quiz will happen on the last remaining day. And yet, when Friday finally arrives and the quiz is handed out, you're genuinely surprised. You never expected the professor to actually follow through with the logic. This is where the paradox reveals its true nature. The prisoner's reasoning is logically sound, but it is also fundamentally flawed. He is using logic to eliminate the possibility of surprise, but surprise itself is inherently unpredictable. By attempting to outthink the warden's statement, he is caught in a loop of self-defeating logic. Now let's consider how the paradox applies to real-world scenarios. Imagine a government agency monitoring potential terrorist threats. They announce that they will conduct a surprise inspection of a facility at an undisclosed time. The facility managers try to predict the day of the inspection by reasoning backward from the last possible day. But in doing so, they inadvertently blind themselves to the possibility of being truly surprised. Or consider a financial auditor announcing a surprise audit of a corporation's records. The company's executives know the audit will occur sometime in the next quarter, but the exact day is unknown. They try to predict the audit based on prior audits, market rumors, and logistical patterns. But when the audit finally occurs, it catches them off guard, not because the logic was flawed, but because the unpredictability was baked into the announcement itself. Now let's return to the prison cell. Imagine the prisoner sitting on his cot, staring at the ceiling. He has reasoned himself into a paradoxical corner, convinced that the execution cannot happen. But what if he stops trying to predict the day? What if he simply accepts that the warden's statement is true, that the execution will be a surprise? In that moment, he breaks free from the paradox. By releasing his need to control the outcome, he rests. Or's the element of surprise. The execution can now occur on any day, and it will genuinely be unexpected. The paradox only exists as long as he tries to eliminate the surprise through logic. The moment he accepts the uncertainty, the paradox dissolves. But this resolution raises a deeper question. If the paradox is a product of overthinking, then how often do we create similar paradoxes in our own lives? How often do we use logic to try to predict unpredictable outcomes, only to end up trapping ourselves in cycles of endless analysis? How often do we mistake knowledge for control, assuming that by reasoning through every possibility, we can eliminate uncertainty? And what if the only way to truly resolve the paradox is to embrace the very thing we are trying to avoid, the unknown? The prisoner's paradox is more than just a logical puzzle. It's a meditation on the nature of uncertainty, a reminder that not every outcome can be reasoned through, not every future can be predicted, not every day can be accounted for. It forces us to confront the limits of logic and the inevitability of surprise. But even as we accept the uncertainty, the paradox remains, a haunting reminder that the mind's desire to predict the future is itself the very thing that blinds us to it. And in that blind spot, in that space where logic and unpredictability collide, lies the very thing we sought to avoid, the unexpected lurking just around the corner, waiting for the moment we least expect it. Imagine you're sitting in a classroom, surrounded by your classmates, when the professor walks in and makes an announcement. Sometime next week, she says, you will have a surprise exam. The day of the exam will be a complete surprise. You will not know the day of the exam until it is handed to you. You sit there, your mind racing. The words complete surprise echo in your head. You look around the room and you can see your classmates' confused expressions. The professor leaves and the room fills with murmurs and whispers. You begin to think it through logically. If the exam is to be a surprise, then you cannot know when it will happen. But what if you try to deduce the day? You start with Friday, the last possible day of the week. You reason, if the exam hasn't happened by the end of Thursday, then it must be on Friday. But if I know it's going to happen on Friday, then it's not a surprise. Therefore, the exam can't be on Friday. Now Friday is ruled out. You move to Thursday. You think, if the exam hasn't happened by Wednesday night, then it must be on Thursday. But if I can predict that, then it won't be a surprise. Therefore, it can't be on Thursday either. Now Thursday is eliminated. You move to Wednesday. You repeat the same reasoning. If it hasn't happened by Tuesday night, then it must happen on Wednesday. But if I know that, it's not a surprise. Therefore, it can't be on Wednesday. One by one, you eliminate the days of the week, using the same logic each time. Eventually, you conclude that the exam can't happen on any day. You breathe a sigh of relief. There will be no exam after all. You can relax. But then on Wednesday morning, the professor walks in, smiling, and hands out the exam. You are completely caught off guard. You are genuinely surprised. But how can that be? You had logically concluded that the exam couldn't happen, and yet here it is. This is the essence of the unexpected exam paradox, a contradiction that arises from trying to predict the unpredictable. It is a paradox of logic and self-reference, where the act of reasoning through the possibilities leads to a conclusion that contradicts reality. Now let's break it down further. The paradox begins with a statement that is seemingly straightforward: there will be a surprise exam next week. But the problem arises when you try to apply logical deduction to a statement that inherently defies prediction. The act of trying to predict the day of the exam creates a paradox in which every possible day is ruled out, yet the exam still occurs. The root of the paradox lies in the conflict between knowledge and surprise. If you can deduce the day of the exam, then it is no longer a surprise. But if you can't deduce the day, then the surprise element remains intact. The paradox is that by attempting to eliminate the surprise, you inadvertently reinforce it. Now let's consider how the paradox plays out in different contexts. Imagine a detective working on a case. The chief tells him, "You will receive a surprise assignment sometime next week." The detective tries to deduce when the assignment will come. He uses the same backward logic, eliminating each day of the week as a possible day for the assignment. By Friday, he has convinced himself that the assignment won't come at all. But on Tuesday, the chief hands him a file with a grin and says, "Surprise." The detective is genuinely caught off guard, despite his best efforts to logically deduce the timing of the assignment. This version of the paradox shows how our attempts to reason through unpredictable events can backfire, leading us to false conclusions and misplaced confidence. Now let's take it a step further. Imagine you are a prisoner on death row. The warden tells you you will be executed sometime next week, but the day of the execution will be a complete surprise. You sit in your cell, going through the days in your mind, using the same backward reasoning as the student in the classroom. You eliminate each day, convinced that the execution cannot occur without contradicting the warden's statement. But on Thursday morning, the guards enter your cell and lead you to the execution chamber. You are genuinely surprised. The warden kept his promise. The execution was unexpected. The paradox reveals itself once again. The very act of trying to eliminate the possibility of surprise ensures that the surprise remains intact. Now let's consider a more psychological angle. Imagine you are in a therapy session and your therapist says, "At some point during this session, I will ask you a question that will completely surprise you." You sit there, waiting, trying to predict the question. Each time the therapist speaks, you brace yourself, expecting the surprise. But as the session goes on, you relax, convinced that the surprise question isn't coming after all. Then, just as the session is about to end, the therapist leans forward and asks a question that completely blindsides you. You are genuinely surprised. The paradox plays out again. Your attempts to predict the surprise only heighten the impact of the unexpected moment. But what is the resolution to the unexpected exam paradox? The key to resolving the paradox lies in recognizing that the act of reasoning through the days is itself a flawed approach. The paradox arises from the attempt to use logic to predict an event that is explicitly stated to be unpredictable. The backward reasoning employed by the student or the prisoner is logically sound but contextually inappropriate. In other words, the act of trying to predict the unpredictable creates a mental loop in which every possible outcome is ruled out, yet the original statement remains true. The surprise is not in the timing of the event, but in the failure of logic to account for uncertainty. But this raises a deeper question. If logic can lead us to false conclusions in situations involving unpredictability, then how much of what we consider to be logical reasoning is actually an illusion? How often do we convince ourselves that we can predict the unpredictable, only to be caught off guard when reality doesn't align with our conclusions? The unexpected exam paradox forces us to confront the limitations of logic and the inherent unpredictability of life. It reminds us that not everything can be reasoned through, not every event can be anticipated, not every outcome can be deduced. Sometimes, the very act of trying to eliminate surprise only reinforces it. And in that space between logic and uncertainty, we find ourselves caught in a loop, endlessly reasoning through possibilities that can never fully account for the unexpected. And so, as you sit in that classroom, staring down at the exam paper that you swore could never come, you are forced to accept the uncomfortable truth that some things in life remain unpredictable no matter how hard we try to reason them away. Imagine you're standing in a crowded marketplace clutching a stack of cash. A man approaches you with a sly grin and offers you a deal. "I have 3 items," he says, holding up a pen, a watch, and a book. "You can choose any one of them for $5. You look at the 3 items and decide to buy the pen. You hand over $5, take the pen, and feel content with your purchase. But before you can walk away, the man stops you. "Wait," he says, "how about this? Would you like to trade the pen for the watch? The watch is worth more, isn't it?" You think about it and agree. You trade the pen for the watch. The man nods and then he asks, "Now, what if I offered you the book instead of the watch? The book is rare and valuable, far more interesting than the watch." Again, you think it over and decide to trade. Now you're holding the book. Then with a smile, the man makes one final offer. "What if I sold you back the pen for just $5? You liked the pen, didn't you?" You agree, pay the $5 and get the pen back. You walk away, feeling as if you've come full circle. But then you look down at your wallet and realize you're $5 poorer. What just happened? This is the essence of the money pump paradox, a situation in which a seemingly rational series of decisions leads to a cycle of trades that ultimately leaves you worse off than when you started. It's a paradox that exploits inconsistency in preferences, revealing how easily we can be manipulated by seemingly logical choices that, when combined, form a costly loop. Now let's break it down further. The money pump paradox is based on the concept of cyclical preferences. In our example, your preference for the pen, the watch, and the book kept shifting. First, you preferred the pen over the watch. Then you preferred the watch over the book. Finally, you preferred the book over the pen. Each individual decision seemed rational in isolation, but together, they formed a cycle that allowed the man to extract money from you repeatedly. Now let's take the paradox a step further. Imagine that instead of just 3 items, the man has a whole collection of objects. He arranges them in a circle, each one slightly better than the last. You go around the circle, trading one item for another, paying a small fee each time. By the time you complete the circle, you're back where you started, but with less money in your pocket. The cycle can continue indefinitely, draining your funds with each round. But why does this paradox work? The key lies in the inconsistency of preferences. In a perfectly rational world, preferences should be transitive. If you prefer A over B and B over C, then you should prefer A over C, but in the money pump paradox, preferences are not transitive. Instead, they form a loop. A is preferred to B is preferred to C, and C is preferred to A. This cyclical pattern allows the manipulator to pump money out of you, exploiting the inconsistency in your choices. Now, let's consider how the paradox plays out in a more realistic scenario. Imagine a gambler at a casino. The gambler has 3 betting options, red, black, and green. Each time the gambler places a bet, they are given a slightly better offer to switch to a different option. The offers are structured to exploit cyclical preferences, encouraging the gambler to keep switching bets. Each switch costs a small fee, and each time the gambler completes the cycle, they are back where they started, but with less money. The casino effectively becomes a money pump, extracting funds from the gambler through a series of seemingly rational, but ultimately self-defeating, decisions. Now let's apply the money pump paradox to a corporate setting. Imagine a company trying to choose between 3 marketing strategies: social media ads, email campaigns, and influencer partnerships. Each strategy seems more appealing than the last, depending on how it is framed. The marketing director keeps shifting the company's budget, allocating funds to one strategy, then another, then another. Each time, the company pays a fee to change its marketing focus, draining resources in the process. At the end of the quarter, the company is back where it started, with no clear direction and less money than before. The cycle of shifting preferences has effectively turned the marketing strategy into a money pump, extracting funds without producing tangible results. Now let's go deeper. Imagine you're a shopper in a mall and a salesperson offers you a deal. If you buy these shoes, you can upgrade to the premium model for just $10 more. You agree, feeling like you're getting a great deal. Then the salesperson says, "Now, how about upgrading to the deluxe model for just $15 more?" You agree again, convincing yourself that the deluxe model is a bargain. Then the salesperson says, "Now, how about going back to the original model? I can give it to you for just $5 less." You take the deal, thinking you're saving money. But by the end of the transaction, you're holding the same pair of shoes you started with, but you're $20 poorer. This is the essence of the money pump paradox, the illusion of progress. Each individual trade seems logical. Each upgrade feels like a step up. But when the cycle completes, you're right back where you started, having paid for the illusion of improvement without actually gaining anything. But what is the resolution to the money pump paradox? The key lies in recognizing the cycle of preferences and breaking the loop. In the original example with the pen, the watch, and the book, the paradox works because the decision-maker fails to see the cyclical nature of the choices. The solution is to step back, identify the cycle, and refuse to participate in the sequence of trades. In other words, the only way to beat the money pump is to refuse to play the game. If you can recognize the loop before it completes, you can stop the cycle before it drains your resources. But this raises a deeper question. How often do we fall victim to money pumps in everyday life without even realizing it? How often do we make choices that seem rational in isolation, but when combined, form a cycle that leaves us worse off? Think about subscription services that lure you in with free trials, then charge monthly fees that gradually increase. Think about shopping deals that encourage you to upgrade to a higher-priced item, only to later offer a downgrade at a discounted price, effectively extracting more money from you. The money pump paradox is not just a quirky puzzle. It's a reflection of how easily we can be manipulated by seemingly rational choices that, when strung together, form a cycle of exploitation. And it leaves us with a haunting question. If our preferences can be so easily manipulated, how many other cycles are we unknowingly caught in? How many other games are we playing without even realizing it? And if the only way to escape the money pump is to refuse to play, then what does that say about the nature of choice itself? Are we really making decisions, or are we just following the cycle, endlessly looping through choices that feel like progress but lead us right back to where we started, a little poorer, a little more exhausted, and none the wiser? Imagine you're sitting alone in your house one evening, scrolling through your phone. It's been a quiet day. You're not expecting anyone, and the night has settled into a calm, predictable rhythm. Then, the doorbell rings. You're startled. Who could it be? You weren't expecting anyone. You get up, walk to the door, and open it. Standing there is a stranger, someone you've never seen before. He looks at you and says, "I bet you weren't expecting me." You nod, confused. "No, I was." "Exactly," he says, stepping forward. "That's why I came." You feel a chill run down your spine. What does that mean? Did he come because you weren't expecting him? Or was the fact that you weren't expecting him the very reason he decided to come? This is the essence of the unexpected visitor paradox, a paradox that plays with the concept of surprise, anticipation, and inevitability. It's a situation where the very act of predicting an event changes the likelihood of it happening, creating a loop of self-referential logic that twists back on itself endlessly. Now let's break it down. Imagine that the stranger continues. "I came because you weren't expecting me, but now that I'm here, you are expecting me. So does that mean I should leave?" You blink, trying to make sense of his words. If the whole point of his visit was to surprise you, and now you're no longer surprised, does that invalidate his purpose for being there? And if he leaves and comes back later, will you be surprised again? Or will the act of leaving and returning cancel out the surprise altogether? Now let's take it a step further. Imagine that instead of one visitor, there are three. Each one is tasked with surprising you at some point over the next week. You know they're coming, but you don't know when. Each visitor wants to catch you off guard, but the more you think about them, the less surprising their visits become. You sit in your house, waiting, anticipating every creak of the floorboard, every rustle of the wind outside. Your nerves are on edge. If the first visitor comes on Monday, you won't be surprised by the second or third. If the second comes on Wednesday, the third visit will be predictable. The very act of waiting for a surprise visit makes the surprise impossible. But then you begin to reason through it. If all three visitors are trying to catch you off guard, then none of them can come on Friday. That would be too predictable. And if Friday is ruled out, then Thursday becomes the last possible day. But if Thursday is predictable, then Wednesday is too. One by one, you rule out each day, convinced that the visits are now impossible. Then on Tuesday afternoon, there's a knock at the door. You open it, and there stands the first visitor, smiling. "Surprised?" he asks. You were so focused on ruling out each day that you didn't consider the possibility that the first visit would happen earlier rather than later. The paradox resolves itself through the very act of overthinking. The more you try to anticipate the visit, the less capable you are of predicting it. Now let's take it further. Imagine you are a security guard stationed at a remote facility. Your boss tells you a surprise inspection will occur sometime this month. You won't know the day or time until it happens. You start to reason through it, eliminating each possible day. If the inspection doesn't happen by the end of the third week, you're certain it will occur in the fourth week. But if you can predict that, it's no longer a surprise. So you convince yourself that the inspection can't happen at all. You relax, letting your guard down. And that's when the inspectors arrive, catching you completely off guard. The paradox strikes again. The very act of trying to anticipate the surprise nullifies your ability to do so. But what if we take it even further? Imagine you're a scientist working on a project with a strict deadline. Your supervisor tells you a surprise audit will occur before the project is due. You try to reason through it. If the audit hasn't happened by the final day, then it must happen then. But if you're expecting it, it can't be a surprise. The paradox creates a loop, a logical knot that tightens the more you try to untangle it. Now let's shift the focus to a more personal level. Imagine you're in a relationship and your partner says, "At some point I'm going to surprise you with a gift." You smile, but now your mind is racing. You start to anticipate every gesture, every comment, every subtle hint, trying to figure out when the gift will arrive. Every time your partner reaches for a bag or smiles at you in a certain way, your mind jumps to conclusions. Days pass and nothing happens. The more you anticipate the surprise, the less surprising it will be. Eventually, you convince yourself that the gift isn't coming. You let go of your expectations. And that's when your partner finally gives you the gift, completely catching why. Oh, off guard. The paradox strikes again. By overthinking and overanalyzing, you made yourself less capable of predicting the very thing you were trying to anticipate. Now let's talk about the resolution to the unexpected visitor paradox. The key to resolving the paradox lies in recognizing that surprise is not a fixed state. It is a fluid, shifting concept that depends on context, expectation, and timing. The more you try to pin it down, the more elusive it becomes. The very act of trying to predict a surprise creates a loop in which each prediction cancels out the possibility of surprise, yet the surprise remains possible precisely because you are caught in that loop. But this resolution raises a deeper question. If the paradox is rooted in our desire to predict the unpredictable, then how often do we fall into similar traps in our everyday lives? How often do we try to anticipate the unexpected, only to blind ourselves to the very thing we are trying to foresee? Think about waiting for a phone call from someone important. The more you watch the phone, the less likely it seems to ring. Or waiting for a job offer after an interview. The more you anticipate the call, the less likely it feels to come. The paradox is everywhere in our relationships, our careers, our everyday routines. And if the very act of anticipation undermines the surprise, then what does that say about our desire to control the future? What if the only way to truly be surprised is to let go of the need to anticipate, to stop trying to predict the unexpected and simply allow it to happen? And what if the real paradox isn't the unexpected visitor at the door, but the endless cycle of anticipation itself? A cycle in which we keep waiting for the surprise that we're convinced will never come, only to be caught off guard when it finally does. Imagine you're sitting in your living room, clutching a lottery ticket in your hand. The numbers are about to be announced, and your heart is pounding. You know the odds of winning are astronomically low, but there's still that tiny sliver of hope. Maybe, just maybe, today is your lucky day. The announcer reads the first number. It's a match. Your pulse quickens. The second number is called, and it's another match. Your mind is racing now, imagining all the ways your life will change if you win. The third number is announced, then the fourth, and finally the fifth. You have every single number. You've just won the lottery. You leap up from the couch, screaming, laughing, crying all at once. You can't believe it. You check the numbers again just to be sure. They're all correct. You really did win. But then, as you look more closely, you notice something strange. The numbers on your ticket don't look quite right. The ink is smudged and some of the digits are barely legible. Your mind starts to spin. Did you misread them? Did you hallucinate the winning numbers? You look back at the TV screen, but the numbers are gone. The broadcast has ended. Now you're not sure. Did you really win, or did you just imagine it? Is it possible that your mind played a trick on you, convincing you that you had the winning numbers when you did? This is the essence of the lottery insanity paradox, a situation where the highly improbable becomes so overwhelmingly desirable that it drives you to the brink of madness. It's not just about the improbability of winning the lottery. It's about the psychological toll of believing that you've won when all the evidence points to the contrary. Now let's break it down further. Imagine a man named Mark. Mark has been playing the lottery every week for the past 20 years. He's spent thousands of dollars on tickets, each time convincing himself that this will be the week he finally wins. But week after week, he loses. Yet he keeps playing, driven by the fantasy that one day he'll strike it rich. One evening, Mark is watching the lottery drawing, clutching his ticket in his hand. The numbers are announced and they all match his ticket. Mark erupts in joy, tears streaming down his face. He's finally won. He rushes to his phone to call his family, but as he looks back at the ticket, he notices something strange. The numbers don't match. They never did. Mark blinks, his heart pounding. Was it a hallucination, a trick of the mind, or had he simply convinced himself that he'd won because he wanted it so desperately to be true? Now let's take it a step further. Imagine a lottery where the prize is not just money, but the fulfillment of a dream. The lottery organizers tell you, if you win, you get to live out your wildest fantasy, but if you lose, you will forget the fantasy ever existed. You buy a ticket and spend days fantasizing about winning. You imagine yourself living in a mansion, traveling the world, becoming famous. The drawing day arrives, and you're convinced you have the winning numbers, but when the numbers are announced, they don't match. You've lost. But now you're faced with a new problem. How do you know that you really lost? What if you actually won but forgot the fantasy as promised? What if the life you're living right now is the life you were living before the lottery, and the life you could have won has already been erased from your memory? The lottery insanity paradox reveals a profound tension between probability and desire, between reality and fantasy. The more we convince ourselves that we're destined to win, the more we become trapped in a cycle of delusion, mistaking our wishes for reality. Now let's apply this paradox to a broader context. Imagine a society where everyone is constantly playing lotteries, not just for money but for jobs, for relationships, for opportunities. Each time they lose, they convince themselves that the next one will be the winner. They keep buying tickets, sinking deeper and deeper into debt, driven by the fantasy that they are destined to win. But the odds are stacked against them. Only a tiny fraction of players ever win, and the vast majority are left chasing an impossible dream. Yet they keep playing, convinced that the next ticket will change everything. This is the nature of the lottery insanity paradox. It's a cycle of hope and despair, a trap that ensnares people in a loop of anticipation, disappointment, and renewed hope. The more they play, the more they believe in the fantasy, and the more devastating the reality becomes when the fantasy fails to materialize. Now let's take a step back and consider a more personal scenario. Imagine a woman named Lisa. Lisa is in love with a man who barely notices her. Every day she checks her phone, hoping for a text from him. Every time her phone lights up, her heart skips a beat. Maybe it's him. Maybe he's finally noticed her. But the text is never from him. It's always from someone else, a friend, a coworker, a telemarketer. Yet Lisa keeps waiting, keeps hoping, keeps convincing herself that the next text will be the one she's been waiting for. Lisa is playing the lottery too, but it's not a lottery for money. It's a lottery for love, for attention, for validation. And just like Mark with his lottery ticket, Lisa convinces herself that the impossible is just within reach, that the next text will be the one that changes everything. The lottery insanity paradox is not just about lottery tickets or gambling. It's about the way our minds latch onto improbable outcomes, convincing ourselves that they are more likely than they actually are. It's about the way we blur the line between fantasy and reality, mistaking the improbable for the inevitable. But what is the resolution to the lottery insanity paradox? The key lies in recognizing the cycle of anticipation and disappointment. The paradox feeds on the gap between desire and probability. The more we want something, the more we convince ourselves that we are destined to get it, even when the odds are astronomically low. Breaking the cycle requires a shift in perspective. It requires acknowledging that improbable outcomes are just that, improbable. It means accepting that the fantasy of winning is just that, a fantasy. It means recognizing that the life we're living right now is the only life we're guaranteed to have, and that pinning our hopes on an unlikely windfall only traps us in a cycle of false hope and inevitable disappointment. But this raises a deeper question. If the lottery insanity paradox is rooted in the desire to escape reality, then what does that say about our lives? Why are we so willing to believe in improbable outcomes rather than accepting the reality of our current situation? Why do we chase fantasies of wealth, fame, and love, even when we know the odds are against us? And if we keep chasing fantasies that will never come true, then how much of our lives are we wasting on illusions? How much time do we spend waiting for the jackpot that never arrives, for the love that never calls, for the life that never begins? And what if the real paradox isn't the lottery itself, but the belief that winning the lottery is the only way to change our lives? What if the real insanity isn't the game, but the way we keep playing it over and over, convinced that this time things will be different? Imagine you're sitting in a dimly lit bar, a glass of whiskey in your hand. The bartender, a grizzled old man with eyes that seem to know too much, approaches you. He places a silver coin on the counter and says, "Watch closely." He lifts the coin between his fingers, twirls it once, and then slams his palm down over it. "Now," he says, "is the coin still under my hand?" You nod. Of course, it's still under his hand. You just watched him put it there. The bartender smiles and slowly lifts his hand. The coin is gone. The counter is empty. You blink, confused. You were certain the coin was there. You even heard the metal clink against the wood, but now it's gone. The bartender reaches behind your ear, pulls out the coin, and places it back on the counter. "Here it is," he says, with that same knowing smile. You shake your head. It's a classic magic trick, a sleight of hand, an illusion. But what if it was? What if the coin didn't just disappear as a trick, but actually ceased to exist, only to reappear later? What if it vanished not just from sight, but from reality itself, only to re-enter existence at a different time and place? This is the essence of the reappearing coin paradox, a situation in which an object seems to vanish and reappear without any logical explanation. It's a paradox that challenges our fundamental assumptions about continuity, causality, and existence itself. Now let's break it down further. Imagine that instead of a bar, you're in your own home, sitting at your kitchen table. You place a coin on the table, stare at it for a moment, and then look away. When you look back, the coin is gone. You search everywhere under the table, across the floor, in your pockets. Nothing. The coin has simply disappeared. You sit back down, frustrated and confused. Minutes pass. Then, without warning, the coin reappears on the table exactly where it was before. You didn't hear it drop. You didn't see it move. One moment it wasn't there, and the next moment it was. Now you're faced with a troubling question. Did the coin ever really exist in the first place? If it did, where did it go? And how did it come back without you seeing or hearing it move? The reappearing coin paradox challenges the very nature of reality. If objects can vanish and reappear without explanation, then what does that say about the continuity of existence? Are objects constantly slipping in and out of reality without us noticing? Are they phasing through different dimensions, only to reemerge at a later time? Now let's take it a step further. Imagine you're sitting in a cafe, reading a book. You place your phone on the table and look away for a moment. When you look back, the phone is gone. You search everywhere, ask the people around you, check under the table. No one has seen it. It's as if the phone simply ceased to exist. You sit back down, feeling foolish and slightly uneasy. Minutes pass. Then the phone reappears on the table right where you left it. You reach out, pick it up, and turn it over in your hand. It's the same phone, same case, same scratches, but how did it vanish and how did it come back? You look around, half expecting to see the bartender from the bar grinning at you, but the cafe is empty. The paradox has now become personal. The coin wasn't just a trick. The phone wasn't just misplaced. Objects are vanishing and reappearing, slipping in and out of existence without any logical explanation. Now let's consider a more scientific angle. Imagine a physicist working in a lab. She's conducting an experiment with a tiny metal sphere, observing it under a microscope. She takes her eyes off the sphere for a moment to jot down some notes. When she looks back, the sphere is gone. She checks the equipment, replays the footage, consults her colleagues. No one saw it move. It simply vanished. Minutes later, the sphere reappears on the lab table, in the exact spot where it was before. The physicist examines it closely, but there is no sign that it was ever moved. No fingerprints, no dust disturbance. It's as if the sphere simply phased out of existence and then phased back in. Now she's faced with a terrifying possibility. What if objects are not as stable and consistent as we believe? What if reality itself is full of tiny gaps, moments where matter ceases to exist, only to reappear moments later? And what if these gaps are not random but follow a pattern we don't yet understand? Now let's take it even further. Imagine you're sitting alone in a room, staring at a clock on the wall. You watch the second hand tick, each movement precise and predictable. Then, for no reason at all, the second hand stops. It hovers in place for several seconds, frozen. You feel a chill run down your spine. Time itself has paused. Then, without warning, the second hand resumes ticking as if nothing happened. You glance around the room, expecting to see something different, some sign that reality itself had skipped a beat, but everything is exactly as it was. Now you're faced with a question that's even more unsettling than the disappearance of a coin or a phone. If time can pause without warning, then how do we know that it hasn't happened before? How many times have we experienced these gaps in reality without noticing? And what if entire moments of our lives have vanished, only to be stitched back together seamlessly, leaving no trace of the void? Now let's return to the bar, to the old bartender with the knowing grin. He's holding the coin again, flipping it between his fingers. "What if I told you," he says, "that the coin never really disappeared at all? What if it was always right here, but your mind just couldn't see it?" You stare at the coin, feeling your grip on reality slipping. If objects can vanish and reappear without explanation, then what else is possible? Are we living in a stable, continuous world, or are we constantly slipping in and out of different dimensions, different timelines, different realities? And if reality itself is full of gaps, full of holes where matter and time can slip away without warning, then how do we know that anything we see or feel is real? How do we know that the ground beneath our feet won't disappear the next time we look away? The reappearing coin paradox isn't just a trick. It's a reminder that the fabric of reality is more fragile than we think, that the line between existence and non-existence is thinner than we imagine, and that everything we take for granted, every object, every moment, every memory could vanish without a trace, leaving us staring into the void, clutching at shadows that were never really there. And as you sit there, staring at the coin in the bartender's hand, you can't help but wonder, If the coin can vanish and reappear without warning, then what else is slipping in and out of existence around you? What else are you missing every time you blink? And if the world itself is full of gaps, full of holes in time and space, then what does that say about the nature of reality? And what if one day you vanish too, only to reappear somewhere else, sometime else, with no memory of where you've been or how long you were gone? Would you even know that you'd been missing? Or would reality itself stitch you back into the fabric of existence, leaving you none the wiser, a reappearing coin in someone else's hand? Imagine you're sitting in a small, dimly lit room with nothing but a pencil, a sheet of graph paper, and a set of simple instructions. You are about to play a game, but it's unlike any game you've ever played before. It's called the game of life, and it's not really a game at all. It's a simulation, a paradox wrapped in a seemingly simple set of rules that leads to outcomes so complex, so unpredictable, that they appear to defy logic itself. The game begins with a grid of squares. Each square is a cell, and each cell can either be alive or dead. The game progresses in steps, and in each step, the cells can either live, die, or come to life, depending on the number of living neighbors they have. Here are the rules. Any live cell with fewer than 2 live neighbors dies, as if by loneliness. Any live cell with 2 or 3 live neighbors continues living. Any live cell with more than 3 live neighbors dies, as if by overpopulation. Any dead cell with exactly 3 live neighbors comes to life, as if by reproduction. That's it, 4 simple rules, nothing more. And yet, as you begin to play, you realize that the game is anything but simple. You draw a few cells, bring them to life, and then step back to watch what happens. At first, the cells move in predictable patterns. They die, they multiply, they form little clusters and shapes. But as you continue to play, the patterns begin to shift. Shapes that once seemed stable suddenly explode into chaos. Clusters that appeared dead come back to life in ways you couldn't have predicted. The game takes on a life of its own, and soon it feels as though the cells are moving of their own accord, following some secret, hidden logic that you can't quite grasp. You are no longer in control. You are merely a spectator, watching as the grid pulsates, expands, and evolves in ways that seem to defy the simplicity of the original rules. This is Conway's paradox. It is a paradox born from simplicity, the realization that a simple set of deterministic rules can give rise to behavior so complex, so unpredictable, that it appears to be driven by free will or conscious intention. Now let's take a step back and think about what this means. Imagine that instead of cells on a grid, you are observing people in a city. Each person follows a simple set of rules. They eat, they sleep, they go to work, they socialize. Each action they take is based on the actions of those around them, just like the cells in the game. At first, their behavior seems predictable, even mundane. But as you zoom out and observe the entire city, you begin to see patterns emerge. Certain neighborhoods become vibrant and active, while others wither and die. Groups of people form clusters, some stable, some chaotic. The interactions become increasingly complex, and soon, the city seems to be alive, moving and shifting like a living organism, following rules you can't quite decipher. The paradox emerges. If each person is just following simple, deterministic rules, then how can the overall behavior of the city appear so complex, so unpredictable? How can simple rules give rise to such complicated, emergent behavior? Now let's take it a step further. Imagine that the grid is not just a simulation but a universe. Each cell is not just a square on a piece of paper but a fundamental particle, a tiny speck of matter. The rules are the laws of physics, and the grid is the fabric of space and time. You start the game with a single cell, a single particle in the void. The particle interacts with other particles and the universe begins to expand. Clusters form, galaxies spin into existence, stars ignite and die. The complexity grows, layer upon layer, until you're staring at a vast, living universe, a universe that started from a single particle following a simple set of rules. This is the heart of Conway's paradox. It suggests that complexity, and even the illusion of free will, can emerge from the simplest of rules, that order and chaos are not opposites but 2 sides of the same coin. Now consider a more personal example. Imagine you are sitting in a coffee shop, watching people come and go. You see a man nervously checking his watch, a woman laughing with a friend, a barista making coffee. Each of them is following a set of simple rules, the rules of social behavior, of routine, of habit. But as you watch them interact, patterns begin to emerge. The man spills his coffee and bumps into the woman, who drops her phone. The barista apologizes and gives them both a free drink. They sit together and soon, they are laughing and talking as if they've known each other for years. A new relationship has formed, a pattern that neither of them could have predicted. And yet, it all happened as a result of simple, deterministic rules. This is the paradox of life itself, the realization that even the most complex, meaningful interactions can emerge from the simplest of actions, that free will might be no thing more than an illusion created by deterministic rules playing out over time. Now let's push the paradox even further. Imagine that you are playing the game of life, but this time you do not control the cells. Instead, you are one of the cells. You move according to the rules, live or die based on the state of your neighbors. You have no control over your own fate, no awareness of the larger grid. From your perspective, everything seems chaotic, random, unpredictable. You don't know why some cells live and others die, why some clusters stabilize while others explode into chaos. But from the perspective of the player, the one who sees the entire grid, everything is following a simple, deterministic set of rules. You are not truly alive. You are just a cell, moving according to predetermined instructions, unaware of the rules that govern you. This is the chilling implication of Conway's paradox. If our universe operates according to simple, deterministic rules, then how do we know that we are not just cells on a grid following instructions we can't see or understand? How do we know that our thoughts, our desires, our actions are not simply the inevitable outcomes of those rules, the illusion of free will created by the complex interactions of simple parts? And if that is true, then what does it mean to be human? Are we truly free, or are we just cells in a cosmic game, acting out a script that was written long before we were born? Conway's paradox doesn't just challenge our understanding of complexity. It challenges our understanding of life, of free will, of existence itself. It suggests that everything we see, everything we do, everything we are, might just be the inevitable outcome of simple rules playing out over time. And as you sit there staring at the grid, watching the cells blink in and out of existence, you can't help but wonder, if life itself is just a game, then who is playing it? And if the rules are already set, then what does that say about us, the cells, the players, the observers, and the game we think we're playing? Imagine you're walking through a dense forest, the trees towering over you like silent sentinels. You come across a fork in the path where two men stand, each guarding a separate path. One path leads to safety and the other to certain doom. You know one thing for sure, one of these men is a knight who always tells the truth, and the other is a knave who always lies, but you don't know which is which. You can only ask one question to only one of them to figure out the safe path. The air is thick with tension as you stand there, staring at them. The knight looks calm and composed, his eyes unwavering. The knave smirks, his arms crossed, his gaze shifty. You clear your throat, your mind racing through the possibilities. What do you ask? This is the essence of the Knights and Knaves Paradox, a classic puzzle that challenges our ability to navigate through lies and truth, to discern what is real when everything is clouded by contradiction. It's a paradox that strips away the noise and leaves you standing face to face with the barebones logic of truth and deceit. Now let's take a closer look. Imagine that instead of two men there are three. One is a knight who always tells the truth, one is a knave who always lies, and the third is a random, someone who could either lie or tell the truth. You don't know who is who. Now the puzzle becomes even more complicated. You can ask one question to any of them, but now the possibilities have multiplied. What do you ask? You stare at them, your mind spinning. If you ask the knight which path is safe, he will tell you the truth. But how do you know who the knight is? If you ask the knave, he will lie, but in a way that you can't easily detect. And the random, he could say anything. The paradox deepens. Now let's step back and think about what this paradox really reveals. The Knights and Knaves Paradox is not just about asking the right question. It's about the nature of truth and deception itself. It forces you to confront the uncomfortable reality that sometimes the truth and the lie are indistinguishable until after the fact. It's about how information can be manipulated, twisted, and reframed to suit the intentions of the speaker. Now let's imagine a slightly different scenario. You're in a darkened room with two doors. One door leads to freedom and the other to a deadly trap. Two guards stand before you. One is a knight and the other is a knave. You can ask one question to one of them, but you still don't know who is who. You decide to ask the knight, if I ask the other guard which door leads to freedom, what would he say? If you're speaking to the knight, he will truthfully tell you what the knave would say, which will be a lie. If you're speaking to the knave, he will lie about what the knight would say, which will also be a lie. Either way, the answer you receive will always point to the wrong door. So you take the opposite door, you walk through it, and it opens into a vast green field bathed in sunlight. You chose correctly. Now let's take it a step further. Imagine that instead of knights and knaves, you're dealing with politicians. Each politician has their own agenda, their own version of the truth. One politician always tells the truth, one always lies, and the third says whatever is most beneficial to him in the moment. You have to make a critical decision based on what they tell you. How do you discern the truth? You can ask one question, what do you ask? This is where the paradox deepens. The truth and the lie are not just about facts and falsehoods. They're about intention, about motive, about perception. The politician who always tells the truth might still tell you something that is technically true but framed in a way that is misleading. The one who always lies might tell you something that is technically false but accidentally reveals a deeper truth. And the one who is random. He might tell you whatever he thinks you want to hear, regardless of its accuracy. The Knights and Knaves paradox becomes a microcosm of human interaction, a distilled version of how we navigate through conflicting information in everyday life. How do you know who to trust when everyone has a motive? How do you distinguish between truth and lies when both can be manipulated to achieve the same end? Now let's push the paradox even further. Imagine that instead of 3 people, you're dealing with an entire society. Some people always tell the truth, some always lie, and some are random, saying whatever benefits them in the moment. You are bombarded with information from all sides, news reports, social media, conversations with friends. You have to make a decision that could alter the course of your life, but you don't know who to trust. Now the paradox is not just a puzzle, it's a psychological prison. You are trapped in a world where truth and lies blur together, where the very concept of reality becomes a shifting, unstable ground beneath your feet. And that's the true nature of the Knights and Knaves paradox. It's not just about finding the right question to ask. It's about questioning everything, questioning what you believe, what you assume, what you think you know. It's about realizing that sometimes the truth is not a beacon of light, but a flickering candle in a room full of mirrors, each reflecting a different version of reality. But what is the resolution to the paradox? The key to resolving the Knights and Knaves paradox lies in embracing the ambiguity. The paradox forces you to confront the fact that sometimes there is no clear path to the truth. Sometimes the truth is hidden behind layers of deception, each layer designed to mislead, to confuse, to obscure. But this raises a deeper question. If we can't trust what people say, then what can we trust? How do we navigate a world where everyone has a motive, where every statement is a potential lie, where every truth is just one version of reality among many? And if the only way to find the truth is to ask the right question, then what does that say about the nature of truth itself? Is it something that exists independently of us, waiting to be discovered, or is it something that only comes into being when we ask the right question, when we frame it in just the right way? And if truth is just a question waiting to be asked, then how many other truths are out there, waiting to be revealed, hidden behind a veil of lies, a mask of deception, a smirk on the face of a knave who will say anything to keep you from finding your way out of the forest? Imagine you're walking through a vast, empty desert. The sun hangs heavy in the sky, and the sand stretches endlessly in every direction. You stumble upon an old man sitting by a colossal stone. The stone is massive, towering above you, casting a shadow that stretches for miles. The old man looks at you and says, "Do you believe in omnipotence?" You hesitate, then nod. "Yes," you say, "an all-powerful being can do anything." The old man smiles, his eyes glinting like shards of glass. "Then tell me this," he says, patting the stone. "Can an omnipotent being create a stone so heavy that even he cannot lift it?" You open your mouth to answer, but the words die in your throat. Your mind is spinning. If an omnipotent being can create such a stone, then there is something he cannot do, lift it. But if he cannot create such a stone, then there is also something he cannot do, create it. Either way, there is a limitation. Either way, the concept of omnipotence collapses under the weight of its own paradox. This is the essence of the paradox of the stone. It's a philosophical puzzle that challenges the very definition of omnipotence, forcing us to confront the logical limits of power, the contradictions inherent in the concept of absolute ability. Now let's break it down further. Imagine you are a philosopher sitting in a darkened room, staring at a blank sheet of paper. You are trying to resolve the paradox, to find a way to reconcile the contradiction. You write down two statements. An omnipotent being can do anything. An omnipotent being cannot create a stone so heavy that he cannot lift it. You stare at the words and they seem to blur and merge before your eyes. How can both be true? If the being is truly omnipotent, then he must be able to create the stone. But if he creates it, then he is not omnipotent because he cannot lift it. But if he cannot create it, then he is not omnipotent because he cannot do everything. The paradox traps you in a loop, a circle of logic that leads nowhere, a snake devouring its own tail. But what if we look at it from a different angle? Imagine that instead of a stone, the being is asked to create a paradox. The paradox is a self-contradictory statement, a statement that defies logic by its very nature. The being creates the paradox, and in doing so, creates a situation in which his own power is called into question. The paradox itself becomes the stone, an unliftable weight that defies even omnipotence. Now let's take it further. Imagine that instead of a stone, the being is asked to create a task that he cannot complete. He creates it, a task so complex, so convoluted that even he cannot solve it. But in doing so, he demonstrates his omnipotence by creating something that defies his own power. The paradox deepens. Can omnipotence include the power to limit itself? And if it does, is it still omnipotence, or is it something else entirely? Now let's consider how the paradox plays out in the real world. Imagine a ruler who claims to be all-powerful. He can command armies, move mountains, bend laws to his will. One day, a peasant approaches him and asks, "Can you create a law so restrictive that even you cannot break it?" The ruler laughs and says, "Of course I can." And so he creates the law. But now he is trapped by his own words. If he breaks the law, he proves that he is not truly omnipotent because he could not create a law that he himself could not break. But if he does not break the law, he proves that he is not truly omnipotent because there is now something he cannot do. The ruler is now caught in his own paradox, a prisoner of his own power. And the paradox reveals a deeper truth, that absolute power is a double-edged sword, a blade that can just as easily cut the wielder as it can his enemies. Now let's take it even further. Imagine that you are a mathematician trying to define the concept of infinity. Infinity is limitless, boundless, infinite in every direction. But then you ask yourself, can infinity contain a limit? If it can, then it is not truly infinite because it has a boundary. But if it cannot, then there is something it cannot do. It cannot contain a limit. The paradox of omnipotence mirrors the paradox of infinity. Both are concepts that defy logic by their very nature, concepts that collapse under the weight of their own definitions. The more we try to define them, the more elusive they become, like sand slipping through our fingers. Now let's return to the desert, to the old man and the stone. The old man is still smiling, his hand resting on the massive rock. So, he says, can an omnipotent being create a stone so heavy that he cannot lift it? You look at the stone, its surface rough and unyielding, its shadow stretching across the sand like a dark wound in the earth. You open your mouth to answer, but once again the words die in your throat. The paradox has no resolution, no simple answer. It is a trap, a snare. Made of words, a question that leads to more questions, each one heavier than the last. But then the old man laughs, a deep, rumbling sound that echoes across the desert. The problem, he says, is not the stone. The problem is the question itself. You frown, not understanding. The question, he continues, is flawed. It asks for the impossible, a contradiction, a logical impossibility. It asks for the existence of a stone that both can and cannot be lifted. It asks for a power that is both limitless and limited at the same time. The question is the stone, and the stone is the question. They are one and the same. You stare at him, and the truth begins to sink in. The paradox is not about the stone. It's about the nature of power, about the limitations of language and logic, about the impossibility of defining the infinite using finite words. The stone never needed to exist. It was always just a question that cannot be answered because the answer itself is a contradiction. And in that moment, you realize that the true weight of the stone is not its size or mass, but the burden of trying to resolve the unresolvable, to answer the unanswerable, to lift a stone that was never really there. And as the old man gets up and walks away, the stone crumbles into sand, dissolving back into the desert, leaving you standing alone with nothing but the empty sky and the echo of a question that still lingers in your mind. Can a being with infinite power create a task so impossible that even he cannot complete it? Or is the true paradox that we keep asking the question, expecting an answer that was never meant to be found? Imagine you're sitting in a small, cluttered study, surrounded by stacks of books and crumpled papers. On the desk before you is a list of words, each written in neat, precise handwriting. The list is divided into two columns. The first column is labeled self-descriptive, and the second is labeled not self-descriptive. You pick up the first word, short. You place it in the self-descriptive column because the word short is indeed short. Then you pick up the next word, long. You place it in the not self-descriptive column because the word long is actually quite short. You continue down the list, sorting words based on whether they accurately describe themselves. The word polysyllabic is self-descriptive because it is a long word with multiple syllables. The word monosyllabic is not self-descriptive because it has more than one syllable. Then you come to the word heterological. You stare at it, feeling a knot tighten in your stomach. Heterological is a word that describes words that do not describe themselves. For example, the word long is heterological because it is not long. The word polysyllabic is not heterological because it accurately describes itself. But what about the word heterological itself? If heterological is a word that does not describe itself, then it must be heterological. But if it is heterological, then it does describe itself, which means it cannot be heterological. And if it is not heterological, then it does not describe itself, which means it must be heterological. You feel the room spinning as the paradox closes in around you. It's a logical loop, a snake devouring its own tail, a question that cannot be answered because the very act of answering it negates the answer itself. This is the essence of the Grelling-Nelson Paradox, a self-referential paradox that traps logic in a cycle of contradiction, forcing us to question the nature of language, definition, and meaning itself. Now let's break it down further. Imagine that instead of words, you are dealing with statements. You are sorting them into two categories, true and false. The first statement reads, "This statement is false." You hesitate. If the statement is true, then it is false, but if it is false, then it is true. The paradox swallows itself, collapsing in on its own logic. Now let's return to the word heterological. Imagine that you are a linguist tasked with creating a definitive dictionary of self-referential words. You decide to define heterological as a word that does not describe itself. You write it down, feeling a sense of accomplishment, but as soon as you step back, the paradox strikes again. If heterological does not describe itself, then it is heterological, but by being heterological, it is actually describing itself. But if it describes itself, then it cannot be heterological. The definition loops endlessly, folding in on itself, creating a vortex of logical contradiction that you cannot escape. Now let's take it further. Imagine that instead of words, we are dealing with people. You are a psychologist conducting a study on self-perception. You ask each participant to write down a single word that best describes them. Some write happy, some write angry, some write confused. Then you ask them to write down a single word that does not describe them. One participant writes sad, another writes apathetic, then one participant writes unself-aware. You pause, staring at the word. If the participant is unself-aware, then how could they accurately describe themselves as unself-aware? But if they are self-aware enough to know they are unself-aware, then they are not unself-aware. The paradox reappears, now in the realm of human identity. Now let's take it further still. Imagine that you are a computer programmer creating an artificial intelligence system. You program the AI to sort data into two categories, relevant and irrelevant. The AI is designed to determine its own relevance based on context, but then it encounters a line of code that reads, "This data is irrelevant." The AI begins to spin in circles. If the data is irrelevant, then it should be ignored. But if it is ignored, then the statement, "This data is irrelevant," is not processed, which means the data might actually be relevant. The AI locks up, caught in an infinite loop, unable to resolve the contradiction. The Grelling-Nelson Paradox is more than just a linguistic trick. It's a fundamental breakdown in the structure of logic itself. It reveals that certain concepts cannot be neatly categorized, that language itself is capable of creating logical whirlpools that suck in meaning and spit out contradictions. Now let's go even deeper. Imagine a society where people are divided into two groups, those who always tell the truth and those who always lie. You encounter a person who says, "I am a liar." If they are a liar, then they are telling the truth about being a Leah. Which means they are not a liar, but if they are not a liar, then they are lying about being a liar, which means they are a liar. The paradox consumes itself, creating a logical black hole that swallows reason and spits out chaos. Now let's return to the study, to the desk covered in words, to the sheet of paper divided into self-descriptive and not self-descriptive. You pick up the word heterological again, feeling its weight, its complexity, its endless loop of contradiction. You place it on the desk and stare at it. There is no right answer. There is no resolution. It is both self-descriptive and not self-descriptive. It is both true and false. It is both a definition and a negation of itself. And that is the true nature of the Grelling-Nelson Paradox, a paradox that reveals the limits of language, the fragility of logic, the boundaries of meaning. It is a paradox that asks a question that cannot be answered, not because the answer is difficult to find, but because the question itself is a trap, a labyrinth of words that lead nowhere, a door that opens into a room with no exits. And as you sit there staring at the word heterological, you can't help but wonder, if language itself is capable of creating contradictions so profound that they defy logic, then how much of what we say, what we write, what we believe, is actually built on a foundation of paradoxes, words that fold in on themselves, statements that cancel themselves out, definitions that define nothing at all. And if language, the very tool we use to understand the world, can so easily collapse into a paradox, then what does that say about the world itself? How much of reality is built on contradictions that we can't resolve? How many truths are actually lies in disguise? How many definitions are just empty shells? How many words are just echoes of themselves, looping endlessly through the void, forever chasing a meaning that was never really there?